Okay, so welcome all the speakers, attendees, those who are interested in the history of the polar climate to our session, past polar climate variability and their teleconnection with the tropics. I am Manish Tiwari from National Center for Polar and Ocean Research with my co-conveners Waliur, Rahaman and Vikash Kumar from National Center for Polar and Ocean Research and Jochen Knies from Geological Survey of Norway, who is also associated with the Arctic University of Norway. So we all welcome you to our session. Well, why this session? Why the teleconnections are important? So for that, I would like to share one picture with you, which fascinates me. So if you can see all this is the global population density, which shows that most of the population lives in the low latitude. The climate change, the most extreme events, the most extreme climate change is happening in the higher latitude, but the population which it affects happens to stay in the lower latitudes, especially in the monsoon dominated region, the South Asian monsoon, the East Asian monsoon. So we have to see that how this climate change which is occurring in the higher latitudes is affecting the lower latitudes. So that is the basic idea behind this session. Now, in this session, since we are looking at how the higher latitudes are affecting the monsoon, so it is a two-way process. Monsoons are also affecting the tropical phenomena are also affecting the higher latitudes. So for that, we have included the monsoon-based studies also. And likewise, the Arctic, the two poles are not isolated. What is happening in Antarctica is affecting the Arctic, and what is happening in Arctic is affecting the Antarctica. For example, there is a very well-known millennial scale asymptoticity between the North and South Pole, which is governed by the AMOC variability. So we have included Arctic-based studies also to look at that. So it will be giving a holistic picture based on the proxy data, model data, and observational-based studies. So considering our large scope, we have received a large number of studies, and obviously we cannot include all for the oral presentation. So there will be a total 17 talks in our session, and they will be in 2 slots, 8 in the first slot and 9 in the second slot. And then there are 5 e-poster presentations as well. Those e-poster presentations are by Devdeep Chakrabarti, Tejeshwar Das, Sarat Chandra Prasad, Doris Velida, and Jindong Jiang. So those e-posters are already uploaded on the SCAR website. So please go and visit those e-posters after the session. And questions can be asked in the question and answer box. And of course, you know by now that all this is recorded. And if you don't want to be recorded, you know whom to contact to do that. And finally, most importantly, the time limit is 10 minutes for the talk and 2 minutes for the question. So basically 12 minutes. After 8 minutes, a prompt will be given. So please go to your most important slide and try to wrap up your presentation. And if time permits, if all the questions cannot be asked after the talk because it takes some time to type, then the questions can be written in the question answer box and it can be taken up at the end of the slot if the time permits. And now, without any further ado, I invite the first speaker of the session, Dr. Thamban Mehlot, who is the senior most scientist at NCPR, to present his talk. Please, Thambanji.
Thank you so much, Manish, for that excellent introduction, the kind of work which I think we are all interested to work in the past as well as modern times as well as in future. My name is Thamban Mehlot. As he already said, I am representing here the team of SIVA project, which is with the 3 PIs, myself, Liz Thomas from British Antarctic Survey, and Penny Matsuoka from NPI, Norway, and the entire team of SIVA project at all these 3 institutions. So the SIVA project standard, essentially we are looking exploring the role of sea ice and westerly winds on the ocean atmosphere exchange of carbon dioxide in coastal Antarctica during Holocene. The SIVA stands for sea ice and westerly winds during the Holocene in coastal Antarctica. So as I said, it's a tri-national collaborative project. So what is the basic motivation for this project? The motivation for this project is actually how Southern Ocean is behaving, currently existing and behaving. Although it's covering about 30% of Earth's ocean surface, the Southern Ocean is a major buffer against the climate change. It absorbs about nearly 75% of excess heat and 40% of the human-generated CO2. from the all entire oceans, which is generally the ocean takes a maximum CO2 out of its 40% is absorbed by the Southern Ocean. However, the Southern Ocean's ability as actually as a sink of CO2 is also changing because of as a result of warming oceans. Because warmer oceans takes always less CO2 in the solubility form. In the left-hand side, you find a picture actually what basically the map of sea air CO2 flux. It shows a clear, kind of there is a large, the blue areas actually are showing essentially a large amount of uptake, and the red areas actually showing the outgassing of CO2. Closer to Antarctica, because of the areas were actually more windy and more sea ice occurring, actually we have more of outgassing, but you can also see a lot of patches where its absorption also takes place. So essentially, the air-sea exchange of CO2 around Antarctica is therefore modulated by the strength and position of westerly winds. Higher the wind, more outgassing, and also sea ice. And because the capping by sea ice reduces the exchange and productivity below the ocean, or in fact the surface ocean around Antarctica. We look at the past variability in sea ice across all around Antarctica, the generalized picture of Antarctica. We have been seeing a consistent increase of the sea ice through time, unlike the Arctic, till about 2016. Suddenly something happened in 2016, which dramatically brought down the sea ice in Antarctica, which has not really picked up thereafter. Because although it expanded by about 2% per decade during all this time of satellite era, it dramatically reduced again. And there have been various theories and as well as the mechanisms attributed to these changes. The most essentially, it's because of the record tropical surface temperature happened during a strong El Nino somewhere in 2015. And also, together with the weakened westerly winds, basically that was related to internal variability of the Southern Annular Mode. Together, these warmed the entire upper ocean in the most part of Southern Ocean, as well as around Antarctica. These warmer ocean temperatures essentially led to the dramatic decrease in sea ice extension. So that's the modern times. Because as you know, the satellite data is only limited about the last 40 years. It does not tell you the entire internal mechanism, internal variability of sea ice, for which you require a long-term period, which is only possible using proxies which are quantitative proxies. In this case, actually, what I'm showing actually is a record of about nearly 200 years of ice core record using which used actually as a proxy. The oxygen isotope variability has been used as a proxy for sea ice variability. What you can see, there's a large internal variability within the system. However, what you see, there have been since last, in fact, the entire 20th century, there has been increasing, sea ice has been increasing. But however, the last several, since 1990s or 80s, actually, there has been a dramatic increase in sea ice around, this is especially around Indian Ocean. I'm talking about the ice core based reconstruction from the Browning Moorland area, from this area, which is actually essentially talks about the history of the sea ice in the Western Indian Ocean of sector of the Southern Ocean. So, and you can also see very well clearly that actually a dramatic change happening very recently also. We look more further actually, it's not only the sea ice, even something dramatically happened on the westerly wind system during the late 20th century. This is another paper actually which is just published in JGR Atmosphere. Wherein you know that atmospheric dust in Antarctica is essentially brought from the other continents, like in South America, South Africa, or sometimes Australia. As far as the Browning Moorland region is concerned, is essentially that dust is, because of the prevailing westerly wind patterns brings from the Patagonian desert. It's one of those ice core record which shows actually a dramatic increase in dust reaching Antarctica since 1980s. So these increases, our study attributed this to an increased aridity over the Patagonian region, as well as the high aridity happening, the increased temperature, as well as high aridity happening in southern South America, as well as the stronger winds during this particular period, which is attributed to the increase, what we call change in shift in SAM, Southern Annular Mode. So there is always an interplay between the El Nino Southern Oscillation, which is essentially a tropical system, and it has a manifestation all around the world. We all know it. And then you have this annular mode around Antarctica, Southern Annular Mode, which is mostly a hemispheric kind of climate system. So these interplay essentially controls the Antarctic climate variability. That is what actually you get in even the proxy record as well as modern times. So thus our studies have clearly shown that the ice core records from the Troning Moorland region, which is this part of the area, essentially provides an ideal site for reconstruction of sea ice and westerly wind system. So why are we interested in this westerly wind system itself actually? Because that's what basically will tell you how did the sea ice, what we call the ocean air exchange of CO2 is happening currently as well as in the past. So thus we come with this project called the SIVA, a trilateral project to drill deep into the bedrock at a coastal ice rise site in Troning Moorland. This could potentially provide a continuous record of on the role of westerly winds and sea ice, the air-sea exchange of carbon dioxide in Southern Ocean for the entire Holocene. The essential hypothesis is that the entire Southern Ocean is a very complicated area where you have strong westerly winds actually driving the Antarctic circumpolar current, and there is a strong easterlies around the land, which is again bringing a lot of moisture to the area. And in between, a lot of things happens. The large amount of eddies, and then there is a polynyas formed in the sea ice. Altogether, this interplay is actually what decides the source or sink of ability of Southern Ocean as a source or sink of CO2. And considering the limited long-term data as well as resultant poor validation models, the only possibility is look at annually resolved ice core records from Antarctic coast. That provides only means for better understanding of the decadal to multi-decadal link between the westerly winds, sea ice, and atmospheric CO2. Why do we require another deep ice record from Antarctica? As we all know that Antarctica, we already have a lot of deep ice core records all the way from inland, lasting about 3 kilometers to some of them about 1 kilometer and so on. Each of them have a different purpose. If you look at the entire Antarctica, how it looked like, from the coast as we go to reaching up to the ice has thickness about 4 kilometers. Whatever happens here is not exactly directly representing what is in the ocean, because what happens in the ocean does not reach there because of the distance as well as of the elevation. So if you want to identify the process actually what's happening in the ocean and that is sea ice as well as wind interplay, we require a coastal site. So we have these kind of what we call as ice domes or ice rises all across along the Antarctica, which has its own local regime, which provides an ideal site for looking at suitable ice core with a high, what we call high accumulation. Therefore, it provides high temporal resolution, as well as it also provides an opportunity to look at the sea ice. So these are preliminary data which came from last year's expedition, which my colleague Vikram Goyal will be presenting in much more detail. We surveyed 2 ice rises along the Troning Moorland region. One is called Waliur, as well as the other one is Cameron. And both are actually surveyed extensively about nearly 400 kilometer long radar surveys using a 2 megahertz ice radar for bed topography and layering, as well as a fern radar for about 200 megahertz radar for stratigraphy and glacial stratigraphy. We also installed an AWS system that actually therefore you have climatic understanding. So I am not going to tell all this, any of the details of the data, which will be becoming showing, except one of this just figure I want to show that actually this is how the radiogram look like, which shows the excellent what you call layering in the ice rise, as well as it's also has a smooth and gentler bed, and the initial age estimate itself suggests that actually at least there is an ice which is more than 11,000 years old, and we are planning to start the building this year, and it will continue for next year. Watch out this presentation from Vikram Goyal in the same session. Finally, I just want to invite you. I'm just completed actually. There's a last slide which I just want to invite you to look at. We are very active in the social media, in Facebook as well as Twitter. Please have a look at it, and we'll keep updating actually the field data as the field photos and field activities happening. We keep on updating them. Thank you so much for the attention. I also acknowledge the Ministry of Earth Sciences, the NERC from UK, as well as Norwegian Polar Institute. Thank you so much. I would be available for question later on.
Maybe 1 minute or 1 minute you can.
Of course, I'm there. I'm available.
So there is a question from Avinash Nair. Is it not better to look at the LGM to Holocene time span rather than just concentrating on the Holocene to better understand the role of sea ice and Southern Hemisphere westerlies on air-sea exchange of CO2?
Yeah, it's something wrong about it. It depends on the time, the time frame which you are looking at actually depends on what exactly you're looking for. If you're looking for a long-term variability, wherein there's already ice core records available, the CO2 records of the sea ice available, although sea ice is not there, but at least the CO2 records are available, which shows this transition as well as the variability happen. What we do not know, there is no continuous record of CO2, especially in the late Holocene, because none of this, the what you call deep ice cores provide that recent time periods. The one which is available in the Lodom, actually it's only again 1,000 years time period actually. Therefore, there is a gap within the Holocene where there is no real continuity of records. And what we aim to understand actually that this during the modern time, means the current interglacial, within that itself we find there is large scale variability. So how, because we are going to have again a further warmer period. So how things have been changing within the warm conditions and what are the real reasons for these changes. So that's the reason actually why we are looking at the entire Holocene. Of course, there is no harm in looking longer time period.
We can move to the next.
Yeah. So thank you, Dr. Thamban, for such a nice talk. And then we move on to the next one, which is by Tariq Ejaj, who will be talking on enhanced warming over drowning mud land during the recent decades caused by coupled interaction between ENSO and SAM. So Tariq. Tariq, are you muted or just check your mic?
Okay, now it's okay.
Yeah.
Okay, so a very good afternoon from India. Myself Tariq Ejaz, and I'm working on Antarctic ice core, mainly temperature reconstruction and, if possible, influence from extratropical and tropical climate mode. So today I'm giving a talk on enhanced warming over drowning mud land during the recent decades caused by the coupled interaction between ENSO and SAM. So
Is there some problem, Tariq?
yes, sir. I think some internet problem. The slide is not.
Just wait. It will get okay. Yeah. Slide shall progress. Now try now. Just try to go to the next slide. Yeah. Okay.
Okay. So now, as we know that the recent increase in the global surface temperature has in the recent few decades, there is an increase in the global surface temperature, and this increase in the surface temperature also influence the remote places of the world, such as Antarctica, and also decreases the stability of the ice sheet, and also which contributed to the sea level rise. So there is a study from Shepard et al. In which they have studied the different part of the Antarctic ice sheet, and they have shown that the two of the Antarctic ice sheet, like West Antarctic ice sheet and Peninsular Antarctic ice sheets, are showing a negative mass balance, whereas East Antarctic ice sheet is showing a slight positive mass balance. There is another study from Bammer et al., in which they have shown that East Antarctic ice sheet is also showing a a slightly negative mass balance during the last decade. So, but this East Antarctic ice sheet has a higher potential for contributing to the sea level rise. So there is an important to study the evolution of temperature in the East Antarctic, particularly in the drowning mode, which has recently shows that temperature is increasing in the past few decades. But if we see for the meteorological data, which is available only for the last 50 years, so anything we have to go beyond the instrumental record. We need to rely on the Antarctic ice core, which has a comparable record of annual resolution to the instrument, and which can be used to calibrate and reconstruct the past climate record of Antarctic or drowning mode region. So now in my study, I've used a new ice core record, IND 33, which was retrieved in the 33rd Indian Scientific Expedition to Antarctica, along with the 3 published ice core record to extract a common signal of delta Atino and reconstructing the past climate of the drowning mode region. So this new ice core is subsampled in our in-house made laboratory maintained at -15°C, and the subsampling is done here. And for the analysis of a stable isotope, I am using a unique laser absorption technology called off-axis integrated cavity output spectroscopy, in which we measure all 3 stable isotopic ratios of water in a single run, and finally processed using the software to get the delta 18O and all the delta D and delta 17O. But in this study, I am focusing on only delta 18O. For for a good paleoclimate interpretation, we need to have a robust chronology. So in this, we have made a rigorous effort to establish a robust chronology using different methods. First, starting with the manual counting of the summer and winter peaks and troughs of delta 18O. And in the second method, we have used a static counter software, in which we use the chemical ions like sodium and chlorine, and also use a volcanic tie point in the form of non-sea salt sulfate. Non-sea salt sulfates means the contribution of sulfate only from the atmosphere, so used as a proxy for the volcanic event. So using these 2 methods, we have established the chronology. At the last, we have also calibrated our chronology with the Tritium peak, which is exact coming as 1962, and using and comparing the chronology obtained from these 2 methods, we have found that uncertainty is only for plus minus 1 year. So now coming to the temperature reconstruction, so we have used the delta 18O record from the DML ice core and IND 33 ice core using a principal component analysis. Delta 18O is dominantly influenced by temperature, and also with some other factors, climate factors like sea ice variability, winds, and the extreme precipitation event. So we need to extract the maximum variability. Therefore, we have used a principal component analysis on the delta 18O record, and we found that the first principal component has a maximum variability, and the maximum variability in the delta 18O comes from the temperature. So we know that. So we have compared our PC1 with the ERA 5 surface air temperature. And we found that there is an excellent positive correlation with the ERA 5 temperature in the drowning mode land. So PC1 is related to the temperature. The second principal component has a 27% variability, which is mainly related to the sea ice concentration, and this is already published in Ejaz et al. In 2021. So using this, using the linear regression equation, which is derived between the PC1 and the era 5 temperature anomaly, we have reconstructed the temperature for the last 200 years, like from 1809 to 1993. So now we need to see the temperature trend. Is there any trend in our reconstructed temperature? So we found that there is a two significant trend which is found in the our temperature record. So from 1809 to 1907, we have a significant decreasing trend. But in the last 70 years, we have found that there is a rapid increase in the temperature from 1942 to 2019. Now, what are the influence of different climate factors in changing the trend of in the recent decade? So we have come to see what are the influence of different climate modes in the drowning mud line. So there are different climate factors which are influencing the Antarctic climate. The first one is INSO, which is a temperature anomaly and has a cyclicity of 2 to 7 years. And the second one is the Pacific decadal oscillation, which is similar to INSO variability, but it has a longer periodicity of 20 to 30 years. And the third one is the Southern Annular Mode, which is the extratropical climate mode variability, calculated as a pressure anomaly from the zonal pressure difference between 40 degrees south and 65 degrees south. So when Antarctica is in low pressure, the SAM is in positive mode and result to the strengthening of westerlies, which influence the climate of drowning mud land. And the last one is the anthropogenic forcing, which can intensify all these above three components. So whether to see is there any influence of all these the climate factors in our record, we have done a spectral analysis of our reconstructed temperature, in which we have used a spectral analysis. So spectral analysis break the time series into frequency and amplitude, which shows a excellent INSO periodicity between 2 to 7 years and a significant periodicity of interdecadal Pacific oscillation between 40 to 20 years. Also, in the wavelet transform analysis, we have seen that INSO periodicities are dominant in the different time span.
Conclude, only 1 minute left, please conclude.
Okay. So now coming to the influence of INSO, we have used a composite anomaly of temperature, and we found that during the El Nino year, there is an increase in temperature of DML region, and the opposite is observed during the La Nino year. Also, we have shown for the heat transport, we have used a vertical heat flux analysis, heat flux analysis, and in the heat flux anomaly, we have found that during the positive during the El Nino year, there is a negative heat flux anomaly in which the heat is moving towards the drowning mud line, whereas opposite is observed during the La Nino phase. So in the last, we have a SAM. We have done a special correlation of Marshall SAM index with our DML reconstructed temperature, and found a positive correlation in the DML region. Also, in the we have compared for the long-term SAM index, in which we combine the SAM with the 20th century SAM with the Marshall SAM index, and see a comparable.
Time up, please. Time up. Stop.
Okay, so in the last, come to the summary, in which we have reconstructed the temperature for the past 200 years, and we found a decreasing trend in the last 1809 to 1907, and recent decade shows an increase in temperature. And in the last, we have found that INSO and SAM are the primary factor which modulate the surface air temperature at the drowning mud land region. So this paper is also accepted recently in the Frontiers in Earth Science. Thank you.
We can move to the next.
Okay, if there is no question, I just have one this thing. Sorry.
Yes, sir.
Yeah. In between, you had shown that delta 18 of variability. So in the periods between 1900 and 1940, there is a lot of variability is there, large amount of variability. Yeah. So this, what can be the reason for this? Did you explore?
I think this one is the Pacific decadal oscillation. We see in this is the oscillation of around 20 to 30 years. So this was also the period. Yes, this one.
Okay.
From 1930 to, but in this we have not in this paper we have not explained the Pacific decadal oscillation. In the later on we will do that.
Okay, great, excellent work. Okay, so Tariq explained that how ENSO and SAM can influence the Antarctic temperatures. So now we will, Tariq, you can shut down stop sharing your screen. So now we will move to the next talk, and I invite Rahul Day, who will be presenting that how the stable isotope ratios of precipitation are controlled. What are the factors controlling those, the stable isotope ratios, a sort of basic talk, so which will be useful for many people working in Antarctica. Rahul?
Hello, I hope you can see my screen.
Yes, yes.
Hello, everyone. My name is Rahul Day, and I'm a PhD student at the National Center for Polar and Ocean Research, India. So if you look at the coastal drawing modelland, the first and the most characteristic feature that you would note is the presence of several small ice shelves and ice rises. So these ice rises are grounded bodies which have their own local flow regime. And what they do is they provide a buttressing effect to these ice shelves, fast-flowing ice shelves, and also the ice sheet. In turn, what they do is increase the stability of the region. So it becomes very important, to understand how the health of these ice rises are responding to the climate change scenario. But why do we need to study these ice rises? So these ice rises, since they're influencing the stability, and they are so close to the ocean that they capture the high frequency maritime variability. So they are an ideal site for an ice core to reconstruct high resolution climate variability. And to understand the climate variability, we need ice cores. So then the question comes, why do we need more ice cores? So if you look at the coastal region, there are not many ice cores which go beyond a century and are of high resolution. The major candidates that you would see over here are S100, IND33, which Tariq was talking about, and IC12. But then these three ice cores also give contradictory results. So if you look at IND33 and S100, they show an decrease in surface accumulation over the past century. But IC12, on the other hand, which is further on the east, it shows that there is a dramatic increase in snow accumulation over the last century, over the 20th century, actually. So that gives a contradictory influence to how the climate regime of this part is changing over time. So for that, we need more and more ice cores based observations so that we can better understand how the climate is actually changing. And to do that, as part of the Indo-Norwegian project MAD ICE, we drilled two ice cores on the Zupran ice rise and Leningrad column ice rise. The Zupran ice rise from the ice core from the Zupran ice rise is 122 meters in length, and the summit of Zupran is at a relatively higher elevation of 325 meters above sea level, while for Leningrad, it sits at a lower elevation of 170 meters, and the ice core that was drilled from here was 50.5 meters. I won't be going into the processing part, how the samples were prepared, as Tariq actually gave you a very good brief of how the sample preparation was done. What I'll be telling you is how these sites are actually a challenge on their own. So these sites being very low elevation, they are prone to summertime melting, which influence the isotopic records, which happens to be the basis for annual layer counting or the chronology of ice cores or reconstruction of temperature and other parameters. Then there is the presence of frequent storm activities, and that makes it difficult to interpret ionic records from the ice cores. So to take up that challenge, we look into line scan images of ice cores, which can tell us about the melt that has been happening and also give us information about the visual stratigraphy. But then this visual stratigraphy has not been studied in the past for fern sections in cores which are from such high resolution and high variability regions. So to do that, we took the 50-meter section of the Zucronan ice core and we performed the chronology using a multi-layer, multi-proxy approach. We took stable isotopes and major ions and did annular counting constrained using volcanic peaks from non-sea salt sulfate records and the tritium anomaly. And what we found is that the visual stratigraphy record that we see has a much clearer and unambiguous record, which can help in sites like this where it is very difficult to interpret annual signals from stable isotopes and ionic records also. Then what we do, we combine all of these proxies and repeat the measurement, repeat the annular counting, and develop a chronology for Zucronan ice core and the Leningrad ice core, IND 36, 9 and 10. So coming to the results, the 122-meter core from Zucronan ice rise, 36/9, dates back to 1725, while the core from Leningrad column ice rise, 3610, dates back to 1865. So if you look at the accumulation record for the common period between these two ice cores, what you'll see is there is a decreasing trend in the ice in the accumulation record, which is consistent with the neighboring ice cores like S100 and IND 33. Even though the rate of change is different for both of these ice cores, but then there is a decreasing trend present. While coming to the stable isotopes, what you'll see is there is again a decreasing trend, that is the delta H values keep getting more and more depleted as we come to us present in over the last century. Again, the rates and the pattern is a bit different from both the ice cores, but then both of them have a decreasing trend. So the first most or the basic conclusion that you might come to is that the temperature of this region is decreasing, and as a result, the accumulation is increasing. But as we all know, the temperature of drowning modelland has been increasing over the last few decades. That's exactly what ERA 5 data also shows. It also shows that the precipitation for this region has been increasing. So which is actually contradictory to what we are observing from the ice cores. So what we do, we also look at the records from a nearby station, Novolazarevaskaya. It has a continuous record from 1961. But what you will see here is that the precipitation record actually shows a decrease. The rate, again, is a bit different. It might be because of the location and other parameters, post-depositional parameters also. But then there is a decreasing trend in precipitation, which is consistent with all the ice core records that we talked about. But then, yeah, the temperature is increasing, but our isotope records show something else. So now, point to consider is that there are three major factors which influence the isotopic values of precipitation: the site temperature where it is getting precipitated, the distance of transportation, and the source conditions. Now, since we confirmed that there is no relation between the site temperature and the isotopic records, we try to find out what about the source and the transportation. To do that, we perform back trajectory analysis for every 6 hours from 1948 to 2016, forced using NCR data. And instead of identifying just the endpoints and the trajectory pathways, we try to identify the locations where there is actual moisture uptake happening from the into the trajectories. So wherever the trajectories are picking up moisture, we are marking those locations. And what you see here is a plot of a logarithmic plot of the weighted frequency of these trajectories. Now, these trajectories were initiated at different elevations up to 5,000 meters. So they have been weighted to show the even out the distribution. And what you will observe is during the summer months, these moisture uptake, they take place very close to the ocean coast. While during the winter months, this happens for these moisture uptake is happening further northwards. And in turn, they are coming from farther away. The same thing we observe for the Leningrad colonized rise also. The region might have a slight shift, but the overall pattern remains the same. To bring this into a more clearer perspective, we combine both the trajectories from Zucronan and Leningrad column, but only for the DJF months and the JJA months. And you'll see that there is a clear differentiation between the source locations, where during the summer months, These moistures are majorly sourced very close to the coast, while during winter, even though not the majority, but a big chunk of this moisture is coming from further northwards. So what happens when the moisture is getting sourced locally or very close by, the distance of transportation is very less, and therefore the isotopic values, they don't get depleted much. But in case during the winters, when they are coming from farther away, the isotopic values get highly depleted and result in more negative values. And then coming to the point that why we are seeing those trends in accumulation and isotopic values, possibly it is because of the changing sea ice cover. So what we have seen on the last few decades, that the sea ice cover has been increasing. And because of that, what is happening, the distance of transportation is gradually increasing. And as a result, the net values of the isotopes, they are decreasing with time. And since the ice cover is also increasing, the amount of open ocean which is available for moisture uptake is also decreasing. And in turn, the net amount of precipitation or the accumulation that is happening has decreased over the past few decades. So what we can do next is actually quantify the influence of the sea ice change cover and on the stable isotopes, and model as to how the moisture uptake from different location and transportation influences the values of the stable isotopes in the ice core records, and whether they can be actually modeled in the observations can be modeled using such transportation values. And in the meantime, as Dr. Kumar has already told you, we'll be heading out to drill a deep core from one of these ice prizes, Kupal or Camel Riggin. Camel Riggin is a better candidate as of now, and Vikram will be telling you about why it is so. So stay tuned. Thank you.
Thank you. Still 1 minute, we can take question, if any. Okay, Rahul, I have a question. So if you have a D-axis data, that these changes should be reflected well in the D-axis data. Did you check that, whether you have?
Yeah, so you're talking about the distance of transportation?
Yes, the related to the fluctuation in the sea ice.
No. So what's happening is because there is a mix of sources here happening. So the d-axis value also doesn't have a very clear signal for the change that we expect. It is there, but it is not so clear. So that is what the problem is, because of the mixing of the sources. So there is a very complex relationship between the isotopic values as well as the d-axis values that we are seeing here.
This is surprising. Means, okay, we can discuss later.
Yeah.
So I also had one doubt, Rahul, that this thing what you are saying, the delta 18, no, it's a general question. The delta 18 reflects the transportation, not the temperature. So it is applicable for ice cores how far into the Antarctica? Whether only to the coast?
No. So what I'm trying to say is, for the sites that we are talking about, they are majorly influenced by this distance of transportation rather than the temperature. It's not a general thing. It's a very local thing which is happening.
Okay.
So we are not saying it's a general thing.
Yeah. Yeah, because most of the ice core interpret delta 18 as temperature proxy.
Yeah, definitely. So that's what I'm trying to say. It's a local thing which is happening for these low elevation sites.
Okay, great. Thank you. Thank you, Rahul. So we will move to the next talk. And the talk is by Lalura CM. The title is An Evaluation of Antarctic Ice Core Nitrate Records as a Proxy for Solar Activity. So I invite Lalu. Lalu, the stage is yours. Please share your screen.
But it's not going that screen.
Till now, it's not visible. Just share it and wait for some time.
Right here.
It's coming maybe.
And not yet.
This one, it's not going.
Maybe you can stop sharing and then again try to share again.
No, the icon is not moving even.
Okay, so maybe you have to wait some this bandwidth problem.
This my video is off, but the trial screen is okay. But there is a screen.
If there is a problem, Lalu, then shall we move to next talk and come after the talk to you?
I didn't even understand what the problem. Because I'm not able to share it because I'm clicking the share this one. It's not moving to where to.
Maybe what you can do now, you can leave and join again, and meanwhile we will do another next talk,
Okay.
and you can come after that talk. Okay.
Okay. Yeah. Fine.
Yeah. So yeah, you can stop sharing and you can leave and again rejoin. So then we will invite the next speaker, and from Antarctica we go to the Southern Oceans, and Vikash is the next speaker, and he will be presenting on that how the southern mid-latitude temperature affects the Indian monsoon, what is the teleconnections involved, and how the two poles, the Antarctica and Arctic, they modulate the southern mid-latitude temperatures. So Vikash, you can share your screen and start with your presentation.
Thank you, sir. Am I audible?
Yeah, you make it full screen presentation mode. Yes.
Close this. Okay. The title of this presentation is Quantitative Climate Reconstruction in the Southern Ocean, Implications to Southern Mid-Latitude Climate and Indian Monsoon Teleconnections. In this work, we connect the Southern Mid-Latitude climate with Indian monsoon. And I will be using the term SML to refer to Southern Mid-Latitude region all the time, which is short for Southern Mid-Latitude. To gain some perspective into or context to this work, we can quickly I will, because this screen is blocking some of my presentation.
It is okay in this site.
Okay, so to gain some perspective, we can quickly look at the time scales at which the monsoon actually varies, and we'll see that there is a spectrum of time scales on which the Indian monsoon actually varies, which we can broadly split into three parts, which is short, long, and intermediate. On the shorter side, we have variabilities ranging from interannual, intraseasonal to decadal to multi-decadal, and which are then again constrained by factors such as ENSO, IOD, monsoon intraseasonal oscillations, interaction of monsoon system with planetary scale features such as Madden-Julian oscillations and AMO. Now, this is also a time scale which is well constrained, means we have a fairly good understanding of variabilities on these time scales, and that is partly because we have actual observation during this period. Now, moving on to longer time scales, we have variabilities ranging from orbital and beyond, which are then again governed by factors such as insolation and event tectonics. And on this time scale also, we have a better understanding of its variabilities, largely because the signal to noise ratio in proxy reconstructed data on this time scale is very good. And that is because we have large variabilities, large amplitude variabilities during this time frame. But we have a problematic time frame in between, which is highlighted in the red sector, which is the intermediate time scales ranging from centennial to millennial, which part of the reason is that we do not get very high signal to noise ratio in proxies, especially qualitative proxies, and because the variabilities themselves are not as strong as they are on the longer time scales. The other thing that comes to mind is that could it also be because of lack of observation in the Indian sector of the Southern Ocean? So if we can look at the global distribution of sediment cores, we will quickly realize that the Indian sector of the Southern Ocean as well as the Southern Indian Ocean is some of the region with least data density. This gets even worse if we consider sediment cores which are material capable of providing samples which can generate quantitative climate records. So with these background in mind, we carried out one study involving a sediment core from the subtropical region in the Indian sector of the Southern Ocean, which is named as ABPS4. As we can see from the age depth modeling, it ranges, it covers last 40,000 years roughly, covering parts of MIS3, the last glacial maximum, the deglacial history, as well as the early to mid-Holocene interval. So we measured magnesium by calcium on carbonates, which were abundantly available on these samples. Magnesium by calcium measurements can be converted, can be transformed into our variable of interest, which is sea surface temperature. In our case, we used a Bayesian inverse model for the mapping our geochemical data to actual sea surface temperature. Now, coming straight to the results, we can see that the figure on the left is divided into three portions. In the middle dotted section, we have our own record, which is compared with paleo simulation from an intermediate complexity Earth system model. On the top, we have compared our record with the records from tropical Indian Ocean, and the panel shown in blue below is where we compare our record with Northern Indian Ocean records of surface hydrography as well as sea surface temperature. Now, the results, salient features of our results were that we observed coldest conditions during the LGM. We got warmer than expected temperatures during MIS3, which we will revisit in later slides. The transition, glacial-interglacial transition was of 4 degrees Celsius magnitude, and we more or less obtained the Antarctic-style deglaciation with features such as HS1 warming and ACR cooling. We also carried out model data intercomparison, where we not only obtained coherence between millennial scale features, but even the absolute values were within the 1 standard deviation range. And finally, when we compared our record with tropical Indian Ocean and the Northern Indian Ocean records, we found that the millennial scale SST variabilities in the Western Arabian Sea and the tropical Indian Ocean matches closely with the reconstructed SML record with features such as HS1, ACR, and Holocene decline. On the other hand, the Eastern Arabian Sea and Northern Bay of Bengal records, which are records of surface hydrography, largely driven by monsoon-induced runoff, also shows a great deal of similarity with our SML temperature data. So expanding on this model proxy intercomparison, we also compared the simulated record with other magnesium by calcium reconstructed SST records from both Eastern and Western tropical Indian Ocean regions on different time frames, and we obtained a reasonably good match despite disparities in the grid scale resolution of the models. So this this enhanced our confidence in using this model further into our analysis. So now coming to this question, what caused more than expected warming in during MIS3, which we not only see in our records, but also the simulated records, which is independently simulated, independent from our own study. And as it turns out that this code is located very close to a region where the Southern Indian Ocean transfers heat and salt into the South Atlantic basin. So if there are changes in heat transfer across this basin, this can get reflected into the southern mid-latitude temperatures, which is connected to this region through the Agulhas return current. To check this further, we computed the east-west gradient in sea surface temperature in the Southern Indian Ocean as well as the South Atlantic basin as a metric for this cross basin exchange, and we observed that this cross basin exchange was greatly reduced during MIS3 when as compared to Holocene, and which means that ARC carried out ARC transferred more heat during MIS3 as compared to Holocene. So one of the reasons why it could happen is because during the glacial MIS3 period, the subtropical front itself can migrate to a northerly position, which effectively reducing the area for exchange between the Indian and the Atlantic basins. So now in this plot, we compare our records with the oxygen isotopic records with in Greenland with the AMOC signal as well as the Antarctic, but most importantly with the Indian monsoon records, and both during deglacial and during MIS3. And we clearly observed that there was a near one-to-one coupling between millennial scale oscillations in the SML SSTs and Indian monsoon variability, which meaning that lower SML SSTs were correlated with enhanced monsoon activity and vice versa. Now, before we go deeper into the data, it's better to look at possible pathways through which the SML climate may interact with the Indian monsoon. So if you look at Indian monsoon, the set of features representing Indian monsoon can be classified into either thermodynamic or dynamic. And meridional thermal gradient is one of the prominent thermodynamic feature of Indian monsoon, which is more so important from a teleconnection standpoint. The dynamical strength of monsoon can be quantified in terms of various metrics, one of which is the vertical shear in zonal winds between 200 and 800 millibars. And this dynamics and this coupling between the dynamics and thermodynamics may not necessarily be stationary, meaning that it can vary over time. In fact, we can measure the strength of this coupling between dynamics and thermodynamics by regressing parameters from the dynamical set with the thermodynamical parameters. So this is also one of the source of uncertainty in our projections of future monsoon projections, because how this dynamics and thermodynamics will be coupled will determine the fate of Indian monsoon going into the future. Because thermodynamically we all understand that monsoon should increase, but then dynamics may reorganize in ways that can actually counterbalance such effects. So looking at how, so there are two pathways that are available to SML for to interact with the Indian monsoon. One involves an atmospheric bridge where SML conditions affect climate conditions in the mascarene high, which changes the cross-equatorial pressure gradients, thereby influencing the dynamics pertaining to Indian monsoon. On the other hand, there can be direct tunneling of anomalies from the southern mid-latitude regions, which can come to the surface in the tropical Indian Oceans, thereby affecting the meridional thermal gradients in the related to Indian summer monsoon. Now, how this dynamics and thermodynamics are coupled will actually determine whether we will be able to figure out which pathway was dominant over other. To check that, we can regress a dynamical parameter alongside a thermodynamical parameter. And this is what we exactly see in the top panel above the dotted line. We can see that the monsoon circulation index, which is just vertical shear in zonal wind, is highly correlated with tropospheric temperature gradient, which is one of the meridional thermal gradients, a thermodynamic feature of Indian monsoon. More so in the glacial period.
Because please conclude.
Okay, sir. So now with this, we understand that it will be very difficult to figure out which pathway was more dominant in SML Indian monsoon teleconnection. So we start comparing our the summer monsoon metrics with our SML SST records when we observe a very high degree of coherence between the two, which suggests the thermodynamic. We also looked at both the thermodynamics and the dynamics parameter during the deglacial period. These data sets are detrended to remove the orbital trend, and we see that there was a high degree of millennial scale coherence between the two. Both in the dynamics and thermodynamics as expected, because we do get a very high dynamics and thermodynamics coupling during the glacial period, during the last glacial period. And finally, we look at the cross-equatorial pressure gradients, which are again compared with which are itself a summer monsoon feature, and compared with our SML SST record, showing high degree of coherence. One thing unique we can see in the deglacial period is that on the orbital scale, they are positively correlated, but their coherence emerges on the anti-correlation emerges on the millennial scale. This can also be seen during MIS3, which lacks any prominent orbital trend, where variabilities are quite anti-correlated on the millennial scale. So with this, I would like to summarize. We generated a first high-resolution record of quantitative paleoceanographic data in the Southern Ocean. We also carried out model proxy intercomparison with our own data, as well as some of the other data in the reconstructed data in the region. And we show that as the southern mid-latitude SSTs were in a big way responsible for the suborbital trends in summer monsoon variability. And we found evidence of both oceanic as well as atmospheric pathways for such teleconnection. Thank you. Am I audible?
Yes, yes.
Okay, okay.
Okay. So,
Yeah,
if there is no question in the chat box, so
I will just stop sharing my presentation.
Okay. So, Lalu, are you back online? Okay, or else we will put your talk at the end after Vikram's talk. So now, since we are in Southern Ocean,
actually, I need to go to some other work, some Delhi also. So I wanted to do fast actually.
Okay, so you're ready now?
I am ready, but this is again the problem. I don't understand because the share screen, what it is showing is select screen.
So you try again this time. Let us see.
Yeah, now it is. You are able
yeah. It is coming now. Put full screen. Yeah.
Okay. Now it's fine.
Yes.
Okay. Good afternoon to all. Actually, I'm sorry because there was an issue with the.
Lalu, your video should be on. Your video,
what?
We cannot see you. Your video.
Okay.
Yeah, we want to see you, na?
It is there. It is.
Huh? Oh, it is there. Anyway, go ahead.
Okay, because I couldn't even understand where this one. Okay, fine. Sorry. Okay, myself, Lalu CM from National Center for Polar and Ocean Research, Goa, India. So I'm going to talk on the topic of evaluation of nitrate record from Antarctic regions. Whether these nitrates can be used as a proxy for solar activity or not, or what are the confidence level this nitrate can be used as a solar proxy from the Antarctic nitrate records. So there are so many longer and short-term nitrate records are available from Antarctica. But however, their interpretation is limited because there are multiple sources as well as the post-depositional effect by the snow to air it is possible. So that will make a difficulty to interpret this nitrate record in a real scientific output. But among the sources, the solar activity related to the production of nitrates is one among the highest number. So as we are aware that when the solar activity is higher, they produces a high number of protons. So these are bombarded with this nitrate and oxygen from the atmosphere and producing the nitrous oxide, that is NOx. We normally call it as NOx. And these are hydrolyzed with the presence of OH ions and deposit and converted to NO3 and deposited in the snow while they are precipitating. So according to this, when this solar activity is higher, so the production of nitrate background in the ice is also high. That is the normal way. But however, all these nitrate records is not showing the signal in the solar activity. That is the difficulties, and that we are going to answer by the following slide. For this case, actually, we have taken an ice core from a coastal zone in Mauland, which is mentioned as 25/B5, and that will represent a time scale of 20th century. It is around 1905 to 2005. That is the exact chronology of that core. So overall, this record show a high temporal variability and high concentration, especially we can see from 1940. That is where we can see from 1940. So, but when we see the accumulation, there is no direct relation between these two also. But in order to understand why this is happened, so this after the 1945 this happened. So, so we conducted the spectral analysis, as well as the wavelet analysis. So when we are seeing, we can clearly see that the periodicity of 11 years, which represents the solar cycle periodicity. And the same we can see in the wavelet analysis also. We can see, especially after the 1914, we can see that the signal very clearly. And similarly, the variance also showing that after 1940 we get the nitrate signal as a very high. And when we are going to the variance representation, the intensity is showing also in the 1940s it is a higher. So we wanted to check what is the relation between the solar activity, and for that the sunspot number is a direct representation of the solar activity. When we are cross-checking, we found that these two are synchronizing very well. When the sunspot number is lower, the nitrate production is high. That is, the solar activity is high when the nitrate production is also higher in that. But before this 1940s, we can see that even the solar activity as well as the nitrate production as in the lower intensities. So what we see in the CDML, we wanted to check it what is happening in the other part of Antarctica. So for this case, we have taken the other available 10 other longer ice core records of nitrate. We have taken and we conducted a similar exercise what we are talking for the CDML ice core, and we found that out of 10 ice core records, the 9 showing the 11-year periodicity very clear, and it was really reflected in this wavelet analysis also. So this clearly showing that it is not only a single ice core phenomena like a CDML, but also it is reflected in the other part of Antarctica also. So to interpret this overall, we conducted the PCA analysis to see what percentage these factors are analyzed. So we found that the factor 1 contributed nearly around 22%, and other the F2 factor is nearly around 18%. So in the coming slide, I will show you what are these F1 factor contributing and F2 factor contributing. So in order to understand this F1 and F2, we conducted the power spectrum analysis the similar way of the factor 1, and we found that the solar signal of 8 to 12 year signal is clearly getting from this picture, as well as one another the 3.5 that is lower, that is representing the ENSO periodicity. So if you check the sunspot, the wavelet analysis, it is clearly showing the 11-year cycle. Similarly, when we taken the nitrate, the wavelet analysis, we can see this is also showing the similar periodicity of 8 to 12-year periodicity. But however, these are not really not the same patch like this the sunspot number. We can see some kind of break in between these periods. So those are the time scale where we couldn't get exactly the solar activity signal in the nitrate record. So in order to understand this on these, we conducted the variant studies for this the nitrate record as well as with the sunspot number. So when we check both for the longer period, we can understand that when these are in opposite directions, similarly what we got in the CDML ice core. So this clearly indicating that this nitrate and the solar activity has a major role in or the really connection between it. But the quantitative interconnection between these two is really tough. So coming to the factor 2, the similar way we have conducted the power spectrum analysis, and we found that especially after the 19th century, we got a higher influence, especially because of the ENSO and this precipitation event. But however, before this period, we didn't get that much signal from this. So that may be due to the biased data from for the ENSO beyond this 1900 or like. But however, we conducted the real-time snow accumulation data from the ice core, and which has been correlated with the nitrate record from all these the ice core which I showed in the before, and we got a high and a strong correlation between these two. So this clearly indicating that the accumulation also have a major role in controlling this nitrate, either by precipitation or by not allowing that the post-dispositional effect. So concludingly, we can say that the power spectrum and relay F1 is concomitant with the solar activity. So that can be used as a proxy for this one. And the F2 factor, which I showed, like the accumulation and the nitrate have a role by either by preventing the post-depositional effect. So coming to the summary, as I told, the nitrate, the CDML ice core, which show the nitrate variability, the high temporal variability during the 20th century, and also the nitrate record shows after this mathematical studies and this, and we understood that the 22% are controlling by the solar activity by this nitrate deposition index, and followed with the precipitation by the ENSO periodicity like 18%. So overall, a total of 40% we can estimate this. However, when we try to find an environmental signature through different processes, this 40% is more than enough to believe or to conclude like we can use it as a real proxy for the environmental climatic event. That is all from my talk. Thank you for listening.
Thank you for being on time. Still, we have a question, 1 minute, 1.5 minutes.
Okay, so if there are no questions, then I have one doubt, Lalu. That is very novel proxy for solar activity, but maybe I missed it. But what is the basic, basic mechanism that connects the solar activity increase and nitrate? Means
okay. Can I talk? Okay.
Yes.
That I talked in the first slide, because during the high solar activity events, there are high energy protons are emitting. So these protons are really hitting or bombarding with the nitrogen and the oxygen present in the atmosphere. So that will create into the nitrous oxide ions.
Right.
So these are the preliminary factors ultimately precipitated in the snow surface.
Right.
So when the solar activity is high, accordingly the number is increasing and the background value of the nitrate is higher. So that is the mechanism. But when we are coming from one proxy, means one phenomena to other, especially the environmental phenomena, we couldn't catch the 100%. So the quantitative measurement still in difficult, but at least around 20%, 22% of contribution is coming from the solar activity. That is what we understood from this study. Thank you.
Great. Thank you, Lalu, for such a great work. And then we again shift back to Southern Ocean. And now you can stop sharing your screen. And now I invite Sunil Shukla to present his work on sea surface temperature reconstruction in the Indian sector of the Southern Ocean over the last 26,000 years. For a change, he is not from NCPR, he is from Birbal Sahani Institute of Paleo Sciences, Lucknow, India. Sunil, please start sharing your screen. Is Sunil there? Hello, Sunil. Looks like Sunil Shukla.
No, I think Lalu, if he doesn't stop the sharing the screen, I think he cannot in.
Okay.
So maybe Lalu is still there, or okay. I think he.
Sunil, if you are there, please try to share your screen. Okay. Okay, maybe we can go to the next talk, and then at the end, we will again invite Sunil. So we shift to the next talk, which is by Pranav Prem, and again in the Southern Ocean, about deep water mass circulation changes in the Indian sector of Southern Ocean during the last glacial cycle. Pranav, you can start sharing your screen.
Yes.
Yeah.
Is it visible now?
Yeah.
Yes, visible.
Okay.
Yeah.
Yeah. Thank you. Good evening, everyone. I'm Pranav. I'm a PhD student at the National Center for Polar and Ocean Research. I'll be presenting a part of my research on reconstructing the deep water circulation in the Indian sector of Southern Ocean using neodymium isotopes. Yeah, here's the schematic of the global thermohaline circulation, and we have deep water formation regions in the North Atlantic and around the coast of Antarctica. During their formation and their movement, they transport heat, nutrients, and carbon dioxide across the global oceans. So any changes in the distribution or mixing proportion and carbon contents of the different water masses making up the global circulation cells are important in forcing and modulating past climatic change, particularly on glacial and interglacial timescales. And to understand the past water mass circulation, we have to use proxies, and in our case, we used neodymium isotopes to reconstruct the past deep water circulation. So neodymium isotopes are used as a promising trace of both present and past deep water circulation because different source areas will have different neodymium isotopic composition, like a fingerprint for each water mass source region. And we can trace the transport of water masses using neodymium, as it has a residence time long enough to stay in the water masses during its movement, but less than the ocean mixing time, so that it can show an interbasinal heterogeneity. The neodymium isotopic composition is expressed as epsilon ND notation, which is the radiogenic isotope neodymium 143, normalized to a standard and multiplied to 10,000. So the more positive epsilon ND values indicate radiogenic values. So here in this figure, the epsilon ND values of the deep water in various ocean basins are shown. In the North Atlantic, the values are around -13.5, and in the Pacific, values are more positive, or we can say more radiogenic, with values between 0 to -4. And in the Southern Ocean, the values are between where the values are intermediate between the Atlantic and the Pacific, around -8 to -9. Here, I will not be going into the neodymium isotope systematics, but let me say that the neodymium isotopic composition is dependent upon the lithology and age of the area. The North Atlantic is surrounded by the older Archean cratons, and this provides the lower epsilon ND. And in the Pacific, the volcanic sediments and relatively younger sediments cause the more positive epsilon ND values to the deep waters in Pacific. And the intense mixing of the above two end members cause the intermediate epsilon ND values for the deep Southern Ocean. So this is our study area. It is located at the southwest Indian sector of the Southern Ocean. And the core is located at a depth of around 4,200 meters. On the right side, the regional hydrography of the area is given. And from these higher oxygen concentrations and salinity contours, we can clearly identify the presence of Antarctic bottom water in our core site. So it should be sensitive to past variations in the Antarctic bottom water. And therefore, the sediments are expected to capture the variability in the bottom water circulation in the Indian sector of Southern Ocean. And this is the neodymium isotopic record we reconstructed from the orogenic iron manganese fraction for the last 156 kiloyears from the Indian sector of Southern Ocean. And also the global benthic delta values are also given at the bottom. These gray shaded regions indicate the glacial marine isotopic stages. And here the modern seawater epsilon ND values of the nearest seawater station is given. And this almost matches with our core top values. And this indicate our record is robust enough to capture the variability of deep water circulation of the region. Also, our record shows the glacial interglacial variability similar to the global pattern of more positive values during the glacials and more negative values during the interglacials. And here I have compared our record with the other deep water records from the Indian Ocean. This red one is our core, and this one is from 40 degrees south, and this green one is from equatorial Indian Ocean. So our sediment core is showing the most radiogenic values and is consistent with the deeper depth and its more southern location. And during glaciers, the epsilon ND values of all the records are shifting to more positive values. And our record and the other record from the Indian sector are getting almost similar values during the glaciers here, here, and here. And this shift to radiogenic values indicate a reduction of North Atlantic deep water reaching to the core sites during the glaciers. In order to get a better idea about the last glacial maximum and the deglacial changes in the Southern Ocean, we have compared our record with the available core records from the South Atlantic and South Pacific for the last 30 kiloyears. Radiogenic values similar to our record reported from similar depths in the Southern Ocean are shown in this figure. This possibly indicates a deep circumpolar circulation with a persistent connectivity between all the ocean basins during the last glacial maximum. Here, I have compared our neodymium isotopic record with the delta 18 from Antarctic ice cores and global carbon dioxide, and along with the winter CS concentration and the sea surface temperature reconstructed from diagrams from our course, which was published in another study last year. Now, if we look at the time of glacial inception, that is around 115 kiloyears, when the delta 18 was decreasing and there is a corresponding change in the global carbon dioxide. But if we look at our deep water neodymium isotopic record at the same time, there is not much variability corresponding to the decreasing global temperatures and CO2. And this indicates that the first decrease in the CO2 was not associated with changes in the deep water circulation. And in the last glacial cycle, the significant changes in the deep water record takes place in here, around in the MIS 5 to 4 transition, and this is corresponding to the changes in winter sea ice concentration and sea surface temperature. And this increase in winter sea ice concentration and a decrease in sea surface temperature shows an expansion of sea ice to more northern latitudes and an enhanced production of Antarctic bottom water due to more brine rejection. And recent studies also shows that shoaling of North Atlantic deep water due to expansion of sea ice, and this can lead to reduced mixing between the southern coastal waters and North Atlantic deep water. Also, in the absence of North Atlantic deep water in the deep Southern Ocean, the deeper depths will be occupied by the recirculated Pacific deep water, and we suggest that these changes cause the shift to radiogenic values in the neodymium isotopic record. And these are the key findings of our research. During glacials, the reduction in the proportion of North Atlantic deep water and a dominant Pacific input to the deeper circulation in the Southern Ocean, and modern circulation times in the Southern Ocean were obtained in the early Holocene. And in the last glacial cycle, significant deep water changes in the Southern Ocean occurred at the MIS 5 to 4 boundary and were associated with changes in the Southern Ocean sea surface conditions. Thank you. Thank you, everyone.
Okay, thank you, Pranav. Thank you for being on time. There is no question in the chat box, so if in the panel, if anybody want to ask.
Even if there is no question right now, people can write in the question and answer box, and at the end of the slot, we will try to take those questions up because it takes some time for typing. So meanwhile, we will move to the next talk, which is by Vikram Goel, and glaciological site survey to determine an optimal coring site in coastal dawning mordland, Antarctica. So we shift back to Antarctica. Vikram, please share your screen.
Sorry, I'm just trying to unmute. Yes. Okay, can you see my screen?
Yes, yes, it is there.
Excellent. So, hello everyone, I am Vikram Goel, and I am from NCPR. And to start with, I would like to discuss, look at this image that we took in December last year in Antarctica. And in this image, you can see two snowmobiles, and they are towing different set of sledges behind, which are actually two different types of ground penetrating radar, or ice penetrating radar as we call them. And they both have, we use them to image the internal stratigraphy within the ice at different resolutions. So one can see all the way to the bed, while the other looks at high resolution to several meters beneath. And in this talk, I'm going to discuss how we are going to use this information to determine an optimal coring site in Antarctica. Okay. Yes, and this work is a part of the SIVA project, which Dr. Thamman has already very well introduced, as well as Rahul. And it's a trilateral project between NCPR, NPI, and the British Antarctic Survey. And so I will not spend too much time in the rationale, but for people who have just joined, I will give you a brief idea. So the rationale is that the Southern Ocean, it absorbs around 43% of the total anthropogenic carbon dioxide and 75% of all the heat. And what controls this exchange is the intensity and the position of the Southern Hemisphere westerly winds. And presently, there is a knowledge gap in the understanding of the global carbon cycle and its interaction with the climate on decade and centennial timescales. And our new project, SIVA, aims to address this shortfall by producing reconstructions of the Southern Hemisphere westerly winds, sea ice, and carbon dioxide at unprecedented resolution. So the key objective, how we are going to do it, is by retrieving ice core from an ice rise which have a relatively high snow accumulation and cover a period of 11,000 years or more. And how we have distributed this work is do a field survey on first year and then followed up by two more field works in which we do the drilling. And in addition to reconstruction of westerly winds, sea ice, and the carbon dioxide, we will also focus on glaciological evolution of ice rises as we are going there. So briefly, I will introduce what is an ice rise. So an ice rise is a grounded ice body surrounded by ice shelf, and it's usually elevated by the surrounding by several hundred meters. So it's surrounded by flowing, slowly moving ice shelf, and then you have an ice rise in between. And the key feature of an ice rise is that it has its own local flow regime. So the ice moves from the summit and goes away to the margin. And what it allows it to have its own look to store past paleoclimate as well as glaciological information within its ice, which can be retrieved by the means of obtaining an ice core or through the radar stratigraphy. So for our SIVA project, we had two candidate ice rises, which we selected based on some preliminary analysis. And last December, we had a team of 4, two our Norwegian colleagues and me and Dr. Bhanu from NCPR. We went to these ice rises and did a lot of survey. So the survey, major part of survey included lot of radar profiling. So these dark red curves shows the 500 kilometer more of radar profiling that we did, both shallow sounding radar and deep sounding radar, as well as we installed several stakes. And we also installed automatic weather station on one of the ice rises. And another key thing that we did, we retrieved 15-meter long fern cores from both these ice rises. And just to introduce to you, this landward ice rise, so the landward ice rise is known as Kamalryggen, whereas the seaward ice rise is known as Kupol-Verblut. So again, in this figure, you can actually see how it looks, the fieldwork. So in this video here, you can see I am pulling the deep sounding radar setup with this is the receiver sledge and the transmitter sledge behind. And then there we have Dr. Bhanu, he's doing the shallow sounding radar survey. And then our Norwegian colleagues here are drilling the 15-meter long course. And also we have the automatic weather station and the stake measurements. So let's look at some preliminary results. So we have these two radar profiles going from west to east, and here for Kamalryggen as well, west to east. And what we see is that both of these ice rises are grounded below sea level. One is around 150 meters below. So Kamalryggen is 150 meters below, whereas Verblut is a bit more deeper. But then they have similar ice thickness of about 500 meters plus. And the most interesting thing that you see from these radargrams firsthand is that we see these features called Rahaman arches. So these upward, these warping arches, we are called Rahaman arches, and they are features that takes a long time to form, and they require the summit position to remain stable. So if the summit position has remained stable, only then we will see this feature. So when we see this feature, it's like a proxy, and we know that this position has been stable. So that is good. And again, like these features tell us the shape, size, and the tilt in these features tell us a lot more information, which we will be working with. So again, like going back to this radargram, so you can see this is the bed here and this is the surface. If you are not familiar with looking at these, so we tracked all the bed throughout all the profiles over the ice rise, and what we get is something like this. So this is the bed elevation map for Kamalryggen and Verblut. These are the gray curves are the actual profiles, and then we have the contour map of the bed elevation. And what we found is that the Kamal region, so this is the summit region of Kamal region, and we see that the summit is somewhat flat, okay, which is what we need. We need a simple ice flow regime for obtaining an ice core. Whereas if you look at Kupol-Verblut, we see a steeply sloping region just east of the summit. So if we have to pick one, just looking at the bed elevation, I think Kamal region is better suited for retrieving the ice core. But there is still more work in progress. So what we are doing now is tracking these internal stratigraphy that we see in the shallow sounding radar. So we can image top 40 meters plus of the fern, and then in these layers we track these layers, and then at present as we talk, our colleagues are actually processing the 15-meter fern course that we obtained from these ice rises, which will be used to date these layers. And with that information, we can get a map of surface mass balance all throughout the ice rise. With this information and the other information from ice thickness, we can we put this information into a 1D ice flow model, which gives us how the age varies with depth all throughout the ice rise. So we get a 3D spatial map of how the age and depth varies across. Beneficial in picking the right spot where to drill. So we'll be doing this analysis for both the ice rises. So if you ask me now, Vikram, can you tell me just what is your guess now? So what we did was we just did the analysis just for the summit region of Kamal region values, and what we found was that I think if you more realistic value, if you look at more realistic value of 27 centimeter per year, we expect to go back to 20,000 years, 75 meters above the bed. So that is, I would say, our the work in progress. And at this depth, we expect to get around 2 to 3 centimeter year per centimeter of resolution, which is also pretty good. So yes, so so once we have the site decided, this year we will go back to these ice rises and we will start with the drilling. So the first thing we will do is we will open the route to this ice rise, shift all the heavy equipment and the camp. So then we set up the camp, and then it will look something like this with the drilling setup. And yeah, start drilling. And before ending, I would just like to highlight that this SIVA work has also already been presented at the RINGS workshop few weeks ago. And the SIVA project aligns, the goals of the SIVA projects aligns very well with the RINGS initiative. And so if you have further question, or if you want to look at the poster that we made for this workshop, it will be presented at the RINGS meeting at these times next week. Yeah, that will be all. Thank you.
So we are very much on time. Means still we have a time. So maybe the first slot is over, I suppose.
Yeah, the first slot is over, but
Hello.
yeah. First of all, Vikram, very nice and beautifully presented. Very nice work and very beautifully presented. Lot of moving pictures and all that. Very enticing. Thank you for that. So if there are no questions, then Vikram can stop sharing his screen. Yeah.
I have a question to Bikram. Bikram,
yeah.
in the age depth model, that calculation, the ice mass loss, so you have a flow, which is a negative term, then ice loss maybe by melting. So those things are taken care of?
I'm not able to hear you, sir.
Okay. So
hello.
I'm asking, am I audible now? Hello?
Yes, sir. Yes, so you're asking about age depth calculation. I couldn't hear the complete question.
Age depth model. So how?
Yes.
Let's say it's a rough estimate or a rough picture of the age depth model, but still. So what are the terms that the negative terms that, let's say, melting, blowing of ice, then ice flow, all these terms are taken care of, or you just based on your accumulation and then you have calculated? And then of course, the nonlinear term you have that the compaction.
Sorry, sir. The connection seems to be bad.
Maybe
so you're
Waliur,
asking
you can type in.
if what I heard was age depth model, and you mentioned something about
Yeah, we can maybe, I don't know, here why the source unstable connection. I don't know. We'll discuss later then.
Okay, so I think Sunil Shukla is still not there. So because his one talk is pending in the first slot. If he's not there, then we will take up the pending questions. So there is one question I can see. Waliur, can you take care of that thing?
No, there is that question already answered by Dr. Thaman Melat. So it was the first question.
I think, okay, I will. I think this question is to Vikash Kumar.
Oh, okay. Vilas,
yeah.
okay. So the second
Yes.
question, yes, the same person. Okay.
Hmm.
So the question is, G. bouloidis calcifies at the roughly 200 meters subsurface in the Southern Ocean. So the temperature reconstructed from the S4 core using G. bouloidis could very well be subsurface temperature rather than SST. So all he's asking that it may not be the representative of SST, it may be subsurface temperature. This is question one. Second question is, what is your takeaway on this? Second question is, reconstructed SST values from the top core S4 looks to be low as compared to the paleo SST from the other studies from the same region. So he has two questions. First is, he is questioning that your reconstructed temperature may not be representative of SST. It could be a subsurface temperature. Second question is, in terms of the amplitude, magnitude, there is a difference with respect to the other cores nearby.
So the first question is, it's very true that the G. bouloidis calcifies at subsurface depths, but the kind of variabilities and the kind of time scales we are talking at, we can take it to be a metric for sea surface temperature itself. Not that we have reconstructed sea surface temperature in its stricter sense, but we are talking about mechanisms which involve sea surface temperature, because because the way through which ocean atmospheric climate system interacts is through the sea surface temperature. So we have taken this planktic subsurface dwelling foraminifera reconstructed temperatures to be a metric of sea surface temperatures on those kind of variabilities and those kind of time scales. As for the second question, I'm not sure with these studies, because when I looked at some of the other records using in nearby records reconstructed using different kinds of proxies, at least the transitions were quite matching with each other. At one point I showed that the glacial-interglacial transition was of 4 degrees Celsius magnitude. That we have found not just in our region, but also spread across that same latitude in other basins also. But exactly, I don't know how much is the difference that Dr. Vilas is referring to.
Actually, there are two papers he has cited. So in
Yes.
that two records, so maybe so probably you can check
So
it.
I look at these records and we'll have a better understanding of what he's exactly asking with this.
Okay. So because I have a question here, you mostly your proxy magnesium by calcium, you assume that it's only the temperature, but then there are some non-thermal effect, for
Yes.
example, pH. So
Yes.
in a Southern Ocean setting, when
Yes.
you have a upwelling, then the change in the upwelling intensity that may reflect the CO2 degassing, pH. So that can also affect the magnesium by calcium ratio. So
Yes, sir, that can affect magnesium by calcium ratio. But while I was telling about how I mapped those values onto actual sea surface temperature, so for that we used a Bayesian inverse model, which takes care of this non-thermal sensitivities. It actually also corrects for things like dissolution as well as pH, salinity. Everything is included in that, and that is why we have that uncertainty band around that reconstruction that we have showed.
Okay, so in the
There
band
is a
gap,
recent paper by Tierney et al. Where they have provided this very nice framework which takes care of these. They have trained their data on a lot of core-top values as well as while conversion, I have factored it my latitude position, CO2 reconstructed pH, CO2 record is taken to be metric for pH as well as salinity, local salinity. Everything was taken care of while converting those values to actual sea surface temperature.
okay, okay, thank you. Then there is.
We have got one more question I can see.
Yes, okay, you can.
Temperature.
It's
Temperature is too large for your.
So I can read out if maybe the word from in the audience they may not see that, so I can read out the question. Question is not your magnesium SST temperature range too large for your downcore variation? How do you explain what is your magnesium by calcium ratios range? So he's telling that your downcore variability is too high. So how do you explain that? And the magnesium by calcium ratio range is also, he wants to know that what is the typical range that one should expect.
Yeah, so one way to look at it is that we look at the when we convert this magnesium by calcium ratio. So if the range is not accurate of magnesium by calcium data, we would expect anomalies in our sea surface temperature itself, the reconstructed sea surface temperature itself. But we find that if I look at my data, it varies. The lowest point is around LGM, which is at 5 degrees Celsius, and at early Holocene levels, it is at 11 degrees Celsius. So this is quite a reasonable reconstruction. So if magnesium by calcium data were off by any means, it would have reflected in the sea surface temperature reconstructions too. So I don't think it is. So your question was, isn't your magnesium by calcium SST temperature range too large for your downpour variation? It is not too large, I would say. We have also carried out this conversion between magnesium by calcium using some of the traditional techniques, and there also we find the range to be very between what is expected at those latitudes. So yeah. Am I audible?
Yes, yes.
So that was my answer.
Okay. Okay. Any other question? I don't see any other questions. So if anybody wants to, still we have some time because there were 2 talks that were not joined in this. So yeah, so we have still time.
So what we can do that we can go to the next slot, and at the end of the second slot. Okay. Okay. So thank you everybody for this wonderful slot 1 of our session. There were many talks on Antarctica and some on Southern Ocean. So we have basically covered the Southern Hemisphere, and there was very healthy discussion as well, especially regarding that Southern Ocean core by Vikash. So now we shift to the Northern Hemisphere, to Arctic and monsoon. And since Jochen is much nearer to Arctic, so I will pass on the baton to Jochen and Vikash to conduct the second slot of our session. Jochen, the stage is yours.
Yes, many thanks, Manish. I take over the second slot of the session past polar climate variability and the teleconnections with the tropics. I just came back from an Arctic expedition and saw the climate changes in the Arctic by myself. No ice, no sea ice at 81.5 degrees north, very unusual. 6 degrees temperatures plus in the water column, and glaciers rapidly decreasing. So it's very timely to see some of the talks here in the session. The first 3 talks actually were a collaborative project we had with Norwegian colleagues from Tromsø and NCPOR and the BSIP in India. And I'm very looking forward to see these results from the talks. We have more talks from the tropical Indian Ocean, from connections and teleconnections with South Asian monsoon during the mid-Pleistocene. The Azore High coupling to the Indian summer monsoon, and then at the end we go back to Antarctica again. So I welcome all the speakers, and we go through the list. I remind you again that we have 10 plus 2 minutes. So after 8 minutes, I think Vikash, you give a sign that we are closing in, and you can give your questions and answers in the chat window and also in the question and answer window. Our first speaker is Waliur Rahaman from NCPOR. And Waliur will present his results from the dramatic reduction of Arctic sea ice in the Arctic Ocean in a time potentially an analog to what we can expect in the future, the mid-Pliocene warm period, some 3.2 million years ago. Waliur, please share your screen with us.
Okay, thank you, Jochen. So, okay, thank you. Basically, the topic again. So now we are Arctic, Northern Hemisphere. So the topic is dramatic reduction in Arctic sea ice during mid-Pliocene warm period caused by northward expansion of Atlantic regime. So basically, this work was carried out it's a collaborative project. So it's a multi-institutional collaborative project, and the project was named, acronym was PACT. So so Indo-Norway collaborative project, and other institute like Leeds from UK, they were also involved. And from Norway side, Jochen was one of the PI in this project. So now, yeah, I don't know. Yes. Okay. Okay, so now we have a very much good satellite observation. In if you see that satellite is everything is now measured by satellite. So if you see the Northern Hemisphere Arctic, and then if you see the Arctic sea ice observation, so you see that in 1984 September sea ice, and then after 12 years in 2016, if you see the sea ice, half of the sea ice is gone. And then there is a almost dramatic reduction. And if the rate is continue, we can see that since 79, we have a satellite record. And then you see there is a continuous decrease. And then if you see that if the rate is continued like this, then there is a model simulation that that is alarming. So that project that the end of the 21st century, Arctic is going to be sea ice free during summer. And then the model that accounted the radiative forcing and then oceanic heat transfer, basically oceanic forcing for this melting or the sea ice loss. And then if you see one thing here in the simulation, that there is a large uncertainty in the end of this century in this projection. So, and then most of the uncertainty is actually coming from the oceanic heat transport, because this component is largely under constraint. So, I don't know what is, yeah. So if you see the oceanic heat transport, that is basically the Atlantic, North Atlantic surface current, which is warm current supplying heat to the Arctic, and then yeah, so that causes actually sea ice melting. So this is basically the oceanic forcing, which is basically nothing but a North Atlantic current supplying heat to Arctic. Now, okay, so the recent studies in science by Waliur et al. Basically, they have deployed the instrument at the bottom of the Arctic sea ice, and they found that actually melting more is occurring from the bottom of the ice. And they hypothesized that actually it's not there is a debate that whether the atmospheric warming is playing greater role or the oceanic forcing, basically the Atlantic heat supply. So they propose that the Atlantification process or the Atlantic heat transport is basically playing the greater role as compared to the atmospheric warming. So this is all about the simulation based on the computer model. But again, there is another approach that you can always do, that is based on the proxy-based reconstruction of the sea ice. So you can go back in time and you can reconstruct based on the proxy. And one of that period in the geological past, which is, we call it mid-Pliocene warm period. This is in a geological interval from this 3.2 to 3 million year. And then during this time, actually the CO2 was almost similar to modern day or near climate scenario. Basically, it's a 425 or 450 ppm of CO2. And then SST was almost 2 to 3 degree higher. So this is exactly the modern day like scenario or near future climate scenario. And that is why it's called is modern day climate analog, particularly this geological interval. So we wanted to test this hypothesis of this Atlantification back in time for this particular interval. So we took a sediment core from the Arctic. This is a the Fram state. This is a gateway between the Atlantic and Arctic. And then we reconstructed the neodymium, reconstructed the North Atlantic, the flow during that time, and then forcing factor, and as well as the sea ice during that time. So neodymium we used, my previous speaker already introduced neodymium proxy, how it used and how it works. So here, if you see the neodymium, basically, so any proxy that you want to employ or use, you have to have a modern day the calibration. So if you see the modern day Arctic, the end member, there are actually basically two component mixing here, which is actually deciding the value of the neodymium isotope at the core site. So modern day, if you see the surface, the water value here, it's a -11, and this is the resulted mixture between the Arctic and Atlantic water. And then the end member of the Arctic is fixed by -10 and Atlantic -15. And if you do the isotope mass balance, so we can see that at this location core site is mixed with a 50% of Atlantic and 50% of Arctic water. So this information that we can go back in time using neodymium isotope, and we can reconstruct the Atlantic transport, basically the volume transport. And if you see, this is a neodymium isotope derived that North Atlantic volume transport. And then you can see this is the modern day, as I said, that the core site modern day, the mixture is almost 50% Atlantic, 50% Arctic water. But in the time when this is M2 glaciation 3.3 million year, at that time, if you see that the flow was almost zero, it's a complete shutdown scenario. So there was no Atlantic flow to Arctic. Whereas during the mid-Pliocene warm period, the flow was maximum. And then it means if you see the eastern part of the Arctic is actually occupied by the Atlantic water. So it's a near almost Atlantification scenario in the eastern Arctic, completely occupied by the Atlantic water. So then let's see what was the sea ice. If you see the sea ice corresponding to this volume reconstruction, the North Atlantic flow reconstruction, if you see that even during the maximum flow of the Atlantic water, when the near almost complete Atlantification scenario in the eastern Arctic, still sea ice was there. So sea ice not completely disappeared. So though there was a reduction by 30 to 35%, but still sea ice is there. So then if you see the model simulation, this contradicts. So our proxy-based reconstruction actually contradicts this model simulation model that predict that almost completely sea ice, summer sea ice free Arctic, whereas we don't see. Though there was a reduction, but still sea ice is there.
8 minutes are over.
Okay. So finally coming to the forcing factor, we found that so we have a radiative forcing basically derived from the CO2 and then the orbital forcing. So we found that our volume transport is actually very much matching with the orbital forcing, which is the eccentricity. So we found that the eccentricity of the orbital forcing actually played dominant role in modulating this North Atlantic flow to Arctic. So to summarize, that during M2 glaciation, we found that there was a complete shutdown of the Atlantic water, Atlantic flow, whereas during the mid-Pliocene warm period, there was a Atlantification, complete Atlantification scenario in the Eastern Arctic. And then we found there was a 30 to 35% reduction in the sea ice, but there was no complete sea ice free scenario during the mid-Pliocene warm period. Now we found that there is a strong coherence with the orbital forcing and then volume transport. So the orbital forcing played dominant role. And our results will validate the model simulation, as well as our results can be used to test the sensitivity of Arctic sea ice to the North Atlantic flow. Thank you very much. And we acknowledge out to the funding agency that provided support to us in the PAC project, Ministry of Earth Sciences, Government of India, and then Research Council of Norway for this work. Thank you very much.
Thank you, Waliur, for interesting talk. There is a question here. Is there any mechanism operating when you say eccentricity controlling the Atlantification during the mid-Pliocene warming?
So it's basically, it's insulations or the seasonality basically that played the role due to the change in the eccentricity, and then you have a more of a so it's you have one in the cold condition, you have a stratified scenario, and the opposite condition happen when you have a increase in the seasonality. Basically, it's a change due to the change in the insulation driven by orbital forcing. So that was the factor for the forcing.
Manish has raised his hand.
So I just had one doubt that you had shown two sources of neodymium isotope, that is Atlantic and Arctic. But what about any terrestrial contribution from hinterland, let us say, or via some erosion, rivers, etc.? So
Yeah,
because
so,
your site is quite shallow.
Yeah, so but still it is below. I would say it's a almost 5,000 meter depth. So at that site, first of all, if you see the modern day scenario, so it is very much with the. So here I will come here to that neodymium here. So if you see the neodymium in the northern side -13, the Atlantic, which is the pure Atlantic water, as it moves towards Arctic, and Arctic, within the Arctic there is -9 more radiogenic value. And if you gradually, we know that modern day, even if you, based on the water flux measurement, based on that, if you do the mass balance, it is modern day composition can be produced with the simply mass balance. So it is at the core site is actually reflecting the mixing of these two water mass, not dominated by the terrestrial weathering signal, because we are at the deeper depth. And if you see the surface water, probably, but even the deeper depth at this core site is it's controlled by the mixing of these two water.
Okay. So
Thank you,
straightforward two-source problem. Okay, thank you.
You can continue the discussion on in the chat if you wish. We can answer the questions later on. But for now, if you stop sharing your screen, Waliur, we can move on to Manish Tiwari, and he will continue to explain us a bit about the Arctic monsoon teleconnections during the late Pliocene. So, Manish.
Okay, so I hope it is visible.
Yeah. If you jump into the presentation mode.
Yeah. Okay, so good afternoon and good evening to everyone. So I will be presenting on the Arctic monsoon teleconnection during the late Pliocene, which is a modern-like warm period, as explained by Waliur just now. And this picture I've already shown, which is the global population density during my introduction to the session. But those who may not have joined at that time, this slide is important because it shows that most of the population lives in the lower latitudes. So we study the high latitude climate, but unless and until we study that how they affect the people living in the lower latitudes, mostly the monsoon dominated areas, only then it will become significant, those studies. So in that case, I am today presenting before you that how the Arctic and specifically Arctic sea ice. What is the teleconnection between Arctic sea ice and monsoon from a proxy data perspective? So we know that the Arctic is changing, the atmospheric carbon dioxide is increasing, there is a change in the global surface temperature in accordance to the CO2 increase, which is resulting in the Arctic sea ice extent decline, and Greenland mass variation is also, Greenland mass is also declining. So the change in global surface temperature is around 1 degree Celsius, has increased around 1 degree Celsius over the last 100 years. But in the Arctic, it is because of the Arctic amplification, it has risen almost by 3 times. So this drastic change in Arctic, is it affecting the monsoon, Indian summer monsoon in some way? So as far as South Asian monsoon is concerned, the model studies have shown that in a warming scenario, the monsoon is projected to increase. So is in the current global warming scenario, there is some linkages between the Arctic sea ice and monsoon. Well, to study this, several observational based studies have been carried out, but those studies have mostly looked at the North Atlantic, basically the AMO and North Atlantic Oscillation, Atlantic multi-decadal oscillation. For example, this is a very famous paper by Goswami et al. 2006 GRL, which have found a strong relation between positive AMO and ISM on multi-decadal timescales. But these studies also did not look at the Arctic sea ice specifically. But of late, recently, some studies have come up which look at the Arctic sea ice extent and monsoon teleconnection. For example, this study by Saurabh Chatterjee, Ravichandran et al., which shows that there is a negative correlation between Arctic sea ice extent and the frequency of extreme ISMR events. Whenever Arctic sea ice extent is lower, at that time, the summer monsoon rainfall extreme events are higher. There is more rainfall, provided the moisture is provided to the Indian region. Likewise, there is another study by Krishnamurthy et al., who have seen that how the summer monsoon events, whenever there are extreme summer monsoon events, the heat is transported to Arctic and it reduces the sea ice extent in Arctic. So the teleconnection is both ways. Arctic is also influencing monsoon, whereas monsoon extreme events are also influencing the Arctic. But again, these studies are mostly based on the past few decades data or based on few events. For example, this was based on few events. So in this case, to see the persistence of this teleconnection and whether they were acting on the longer time scales, we can take the help of proxy data. So proxy evidences do exist. There are many studies. Just to give you one example, there is a study by Duplessis et al. 2014 paleoceanography, where they have seen compare the global monsoon, that is the East Asian monsoon, the South Asian monsoon, the African monsoon, the North American monsoon, with the North Atlantic temperatures. And they have found whenever the North Atlantic temperatures were lower, the monsoon was weaker, it was more arid, shown by these green, blue bands. But again, this looks at the North Atlantic temperature, but not at the Arctic sea ice as such. And there are other studies also which shows that how the tropical convection, the monsoon, is affecting the North Atlantic and the higher latitudes. For example, we published a paper in Quaternary Research where we showed a teleconnection among high latitude climate, denitrification, and global monsoon. That is, variations in tropical convection affects the atmospheric moisture content and emission of greenhouse gases, which in turn influence the high latitude climate. But with Arctic sea ice, still not much information is there. And also these studies were mostly limited to the past 40-50,000 years, maximum going to the last interglacier, 125,000 years or so. But when we see the CO2 concentration, this is the present CO2 concentration. We have crossed 415 ppm. But when we see the past, this is the EPICA ice core CO2 record, we see that during the last 800,000 years, we never had such high concentrations of CO2. So to understand the present climate, to understand how the monsoon is going to act in the present global warming scenario, we need a modern day analog. And such a modern day analog is provided by the mid-Pliocene warm period, which Waliur has just explained. So it is the recent most period when the tectonic setting and CO2 were similar to present. This represents the CO2. This is the MPWP around 3 million years ago. It is quite recent. 3 million years from may appear very old, but on geological time scale, which is 4,600 million years old, 3 million years is quite recent. So it is quite recent event. And at that time, the temperatures, the annual global mean surface temperature were higher by 2.3 to 3.4 degrees Celsius, and sea level was higher by 20 meters. So studying mid-Pliocene warm period can tell us that how the monsoon is going to behave in a continued global warming scenario. So this study was, as Waliur and Jochen has already told, were done under the auspices of Pliocene Arctic Climate Teleconnection Project. That is a PAC project, which is a joint Indo-Norwegian research project, in which we had studied ODP cores from the Arctic, from Arabian Sea, and from Australia, near Australia. So today I will be presenting my studies on my findings from the core IODP 355 and trying to relate it with the Arctic sea ice concentration done by Rahaman et al. So this is the study site, IODP Expedition 355. There are two sites were drilled, U1456 and U1457 on board the JOIDES resolution, in which I participated as an inorganic geochemist. And in this study, we have used multiple isotopic and geochemical proxies, delta 13C and delta 15N of sedimentary organic matter, total organic carbon, nitrogen concentrations of sedimentary organic matter, and major and minor elemental concentrations, which were all measured in NCP or in our various laboratories. Well, in around a couple of years back in 2017, we published a coarse resolution record of denitrification and Indian summer monsoon from this IODP 355 core sites. And we found that during the MPWP, there was a signature of increase in monsoon and denitrification. So we thought that it would be better, it would be interesting to study this period in higher resolution, considering its importance. So we carried out higher resolution study in this time period. So here are the results: high resolution monsoon reconstruction from the late Pliocene, including the mid-Pliocene warm period. So we find stronger monsoon precipitation during MPWP, and I will also discuss the role of Indonesian through flow. So here in this figure, the bottom represents the age. You can see it starts from 2.7 million years to 3.4 million years ago, which is the late Pliocene. The top panel represents the denitrification, delta 15N. The panel B and C represents the productivity, TOC and total nitrogen. And the panel D represents the chemical weathering. All these are related to the monsoon strength. And finally, we compare it with the... What is that?
8 minutes are over.
Okay. So here we can, then we can see here that we can vary, the proxies are very well divided into 4 time periods, 1, 2, 3, 4, where the 3 represents the mid-Pliocene warm period. And we see that proxies very clearly show that monsoon was stronger during the mid-Pliocene warm period, whether it is denitrification, whether it is TOC, whether it is total nitrogen, there's a productivity proxies, or whether it is totally independent chemical weathering proxies of potassium by aluminum. But then we find that the monsoon suddenly increases during at around 2.95 million years. In fact, that was interestingly a period of intensification of northern hemisphere glaciation, and that intensification led to should have led to the decline in monsoon, but we find that monsoon is increasing. So this we found out that it is because of the influence of the Indonesian through flow. At that time, around 2.95 million years ago, the tectonic northward shift of New Guinea source water of Indonesian through flow changes from warmer South Pacific to colder North Pacific, which is explained in the Sarat Chandra Prasad et al. 221 PPP. So these colder waters led to the enhanced interhemispheric temperature gradient and pressure gradient, which led to the increase in monsoon. So this 2.95 million year strengthening of monsoon can be explained by the ITF. So we further checked our proxy data using a simulated regional precipitation data using the Aussie layers. And here we see that this is a independently simulated data. So here we see that the monsoon precipitation. So basically it shows the composite between the MPWP, that is the period third, and periods preceding and succeeding it. So the period, when we see the difference in the precipitation during MPWP and the period preceding it, we find that the precipitation increased over the Western Ghats and over the core monsoon zone, but the precipitation got weaker over the Indo-Gangetic Plain and Northeast and Southern India, parts of Southern India. Likewise, when we compare the composite precipitation during MPWP and the period after it, we again find the precipitation was higher during the MPWP and over the Western Ghat and over the core monsoon zone, but it was less due over the Indo-Gangetic Plain, and so there were drought-like conditions. So what is interesting, it matches very well with the modern data. So this is the modern data. It is from Roxy et al. 2005 Nature Communication. And it also shows there is a what you call oxbow horseshoe-like drying pattern there is enhanced monsoon over Western Ghats, over the core monsoon zone, but weaker monsoon and drought condition over the Indo-Gangetic plain, which we are experiencing in this year also, in fact, and over northeastern part and over the southern India. And when we see our MPWP differences, then we find that it very well matches with the modern precipitation data. So MPWP can act as a very important period for deciphering that how monsoon is going to behave in a global scenario, a global warming scenario. And then since the time is less, so I will try to cover it fast. To explore the role of Arctic sea ice, we need to look at the various processes which are affecting the monsoon. Monsoon is a very complex process, is affected by thermodynamic and various dynamic effects, which Vikash has touched in his presentation. Now, thermodynamic effects are any effect which affects the specific humidity, which is basically the global temperature change due to PCO2 variability. So we have here compared our data. This is our delta 15N, which represents the proxy data precipitation. And here we have compared it with solar insolation with the sea ice reconstruction from Rahaman et al. 2020. This high resolution sea ice reconstruction allowed us to compare our precipitation reconstruction with the Arctic sea ice. And then we compared with the PCO2 data and with the global glacial-interglacial cycles. And then there are dynamic factors which causes variation in the atmospheric transport of the water vapor, which is because of non-uniform temperature change. So it causes ITCs and migration. Anything orbitally modulated insulation, Arctic mostly precision, Arctic sea ice extent, SST, all this can cause this sort of dynamic effects. So monsoon is what we see. The monsoon variability is basically interplay of the dynamic and thermodynamic effects. We have tried to compare it, and okay, so now I'm not able to change my slide.
You should conclude, Manish. We are over time.
Yeah, the thing is I'm not stuck somehow. So maybe. So it looks like some mechanism is that if you over time, your slides get stuck. You cannot move.
No. Then it's time to conclude.
Yeah. So yeah, basically I'm not able. I have to stop sharing. Yeah, looks like I have to stop sharing. And just give me a second. I will just go to my takeaway messages. So basically, because of the time limitation, what we find that during the lower Arctic sea ice extent leads to stronger late Pliocene South Asian monsoon. And anybody interested in this can contact me. My email is there. And so finally, the takeaways are there that during the late Pliocene, there are two distinct intervals of monsoon intensification, MPWP and 2.9 million years ago. Lower Arctic sea ice extent, a stronger Pliocene South Asian monsoon. And in the future, with continued warming and declining sea ice extent, more intense precipitation, though regionally varying, will be there. With this, I finish my talk. Thank you.
Thank you very much, Manish. Unfortunately, we have no time for additional questions, but you can send in the chat or ask in the question and answer window. So we continue. And I welcome Padmasini Behera, also from NCPOR, I think. And she continues on the Arctic stratification during the mid-Pliocene warm period. Please, Padmasini, if you would like to share your screen. I can't see you. I can't hear you.
She has told that please add me in panelist. Padmasini has requested to be added here as a panelist. So maybe the technical team can add her as a panelist.
Yeah. If this takes maybe time, we can wait until the end of the session and give Padmasini the opportunity to present her talk. Perhaps the IT team can help to let her in.
So I am here.
No, we can hear you.
She's there.
Yes,
Hello?
if you, hello, yes, you can share your screen if you wish, we can hear you.
Yes.
Yes,
Can you see the slides?
yes, if you go into the presentation mode.
Is it visible properly?
It's not easy to hear you, so get closer to the microphone.
Hello? Here? Is it audible now?
We are not seeing the presentation in the presentation mode. So if you,
Yes. It is in presentation mode only.
You can go to slideshow.
Yeah, I have done that.
Can you go to slide screen mode, please?
Is it visible properly now?
no,
Could you try again, please?
I'll stop sharing, then I'll start again.
You have already stopped your sharing. You can start now.
Is it visible now?
Go to the presenter mode.
Yes, I have done that.
Move your slides. No, it's not moving.
no.
Not moving.
Can you send us this PPT to us? We will share it as a screen, and if you want, we can change the slide from here. Are you uploading or not?
Yes. Yes, sir.
Meanwhile, maybe we can move to the next presenter.
Yes, we can wait and you maybe sort out the technical problem. I would suggest that we move on, and Padmasini will talk at the end of the session. So the next speaker is Samuel S.K. on the assessment of the relationship between the solar irradiance on the atmospheric rivers and associated precipitation over the Arctic region. So I would like to give the word to Samuel, if he is in the panel list. Samuel, are you here?
No, Mr. Samuel is not here.
Mr. Samuel is not here. Okay. Then we have a following speaker, which is Rajesh Saraswat on the tropical Indian Ocean contribution to the last deglaciation. Is Rajesh in the panel?
Yes, I'm there. Okay, and I'm here.
Very good. I give you the word. Please share your screen.
Thank you so much. I'll just share my screen. Can you see the slides now?
Yes, very good. Go ahead.
Thank you so much.
Mm-hmm.
There are a lot of talks about the connection between the Arctic and Antarctic, as well as the tropical Indian Ocean. And this talk also is about a similar discussion, how the tropical Indian Ocean might have contributed towards the deglaciation. We know in the paleoclimatic studies, deglaciation is one of the important topics that we often try to figure out. How come there were these long glacial intervals and then a comparatively brief deglaciation, followed by a brief interglacial and then again going into glacial. So what led to these glacial interglacial cycles? What led to the termination? There are different hypotheses given for that. And basically the way we talk about the deglaciation is that there is a reduction in the ice sheets in both the Arctic and Antarctic region. And at the same time, there is also a change in the seawater temperature throughout the oceans, much less in the equatorial region and relatively more as we move towards the higher latitudes. At the same time, this is just a comparison of how the condition was during the last glacial maximum, which is supposed to be around 19 to 24 kilo years back, as compared to the early Holocene time around 11,000 years back. Now, there are different hypotheses given for the deglaciation. People try to figure out what actually causes these deglaciations. And in these hypotheses, there are insulation, which is often talked about, one of the drivers, but that doesn't seem to be really giving us the complete clue about the deglaciation because of the small change on the 100 kilo-year cyclicity. We also talk about the changes in the radiative force, basically because of the change in the greenhouse gas concentration, mainly the the change in the carbon dioxide and methane. But still, there are records once in a while which suggest that probably the greenhouse gases were not responsible for the deglaciation, or rather the triggering the deglaciation. Like, for example, in this record, it's an average of the northern hemisphere temperature as well as the southern hemisphere temperature and the carbon dioxide concentration, atmospheric carbon dioxide concentration. Now, we do see that in the tropical Indian Ocean, the warming starts almost 1 kilo year prior to the change in the atmospheric carbon dioxide concentration anywhere. That means there are several other factors which might trigger the deglaciation rather than simply looking at the change in atmospheric greenhouse gas concentration. Now, when it comes to the tropical regions, it's an increased emphasis now to figure out whether the tropics had anything to do with the deglaciation. There was this really interesting paper wherein people talked about the deglaciation and sea ice variability, especially in the European ice sheet region, because of the changes in monsoon pattern, because it brings in a relatively denser and saline Mediterranean water, which is then transported further up north, and then it increases the moisture availability, and that's how it controls the European ice sheet region. Of course, there are other modeling studies also which suggest that probably the tropical oceans are important when it comes to the northern hemisphere deglaciations. So we also try to look at whether the tropical Indian Ocean in any way contributed to this deglaciation. So looking at the tropical Indian Ocean, it's a very, very dynamic region, part of the warmer Indo-Pacific. The temperature remains higher than 28 degrees centigrade throughout the year, and that leads to some of the major processes over here, the Walker circulation, the El Nino Southern Oscillation. All these processes happen in the tropical Indian as well as Pacific Ocean, and that in turn affect the climate on a very, very large scale. So now Indian Ocean itself has been, now it's realized that there are several processes which are unique to the Indian Ocean, like, for example, the dipole mode in the tropical Indian Ocean, which supposedly affects the variability itself in the Indian Ocean and its connections with other parts of the other world oceans like the Pacific as well. So it's an important phenomena which was discovered in late 90s, the dipole mode. So that again points out that the Indian Ocean might be playing, or the tropical Indian Ocean might be important as far as the global climatic processes are concerned. So looking at that, we collected a core from so almost equatorial Indian Ocean or the southeastern Arabian Sea. It was collected during the 4th expedition of Sindhu Sadhana. There were gravity core collected at a water depth of around 1540 meters. And we generated the elemental as well as the planktic foraminiferal census count data, as well as stable isotopic ratios of the surface dwelling planktic foraminifera on that core. The core covered in detail the last around 24 kilo years, and we looked at detail during the termination time that this core covered. The core was very well dated by using the AMS radiocarbon dates on the surface dwelling G Ruber as well as the Cyclifer. What we saw that there is a strong and very distinct glacial-interglacial variability. And we also see a strong, a large change in the relative abundance of the Globigerina boloides, which is an upwelling indicator because it prefers comparatively colder and nutrient-rich waters. We also see a strong variability in the barium by calcium ratio, which is a proxy for the terrestrial runoff, because the increased runoff leads to increase in the concentration of barium, and then the barium by calcium ratio of the foraminifers increases in comparison to that. We also looked at the organic carbon variability as well as the magnesium by calcium. We used it to understand the temperature variability. Now, looking at the unique changes in this record, we tried to figure out whether the changes what we are seeing here, are they something unique to this core, or we do see something similar in other cores collected from the tropical Indian Ocean. Yes, the variability seems to be in line with other cores which have been published from the equatorial region as well as the Bay of Bengal and Arabian Sea. We do see a variability of around 3 to 4 degrees centigrade on last glacial maximum to early Holocene. But what was unique in this core was that this early warming prior to the actual beginning of the deglacial warming. And we do see the signatures of this warming prior to the deglaciation in some other cores. Of course, not the intensity and the duration varies, but then there are signatures in other cores also of this warming. I'll be coming back to this anomalous warming prior to the deglaciation in the later part of the talk. Of course, we did see a similar pattern in the monsoon-derived Day-18 signatures on this core with the other cores collected from the nearby regions. So what we want to emphasize upon in this particular picture is that the variability during, of course, from LGM to the early Holocene, but prior to the LGM. Prior to the LGM, we do see a distinct increase in the sea surface temperature. This increase is around 1.5 degrees centigrade. It is quite distinct. We have looked at the average variability also, and in some other
8
nearby.
minutes are over.
Okay, thank you. The other unique property, feature during this early deglacial warming was the strong upwelling event, which was confirmed with the increase in both the organic carbon as well as the relative abundance of upwelling indicator G boloides. So what was it that caused this early deglacial warming prior to the actual warming that started at around 18.2 kilo a year, which seems to be basically driven by the increase in carbon dioxide concentration. Now, interestingly, this increase in the upwelling indicator boloides as well as the warming was accompanied by an increase in the PCO2 from contribution from the from the Arabian Sea as well. And then we do see at the same time strengthening of the MO. Now that made this entire thing quite interesting. That was it the increase in the sea surface temperature and upwelling in the Indian Ocean which led to the strengthening of this MO. Then we tried to figure out how is it possible. Now, looking at the way it can be done is that there are several modeling studies which suggest that if the tropical Indian Ocean warms, it triggers a gill-type atmospheric teleconnection which warms the tropical Atlantic, and it suppresses the monsoon in that region. If the monsoon suppresses and the temperature increases in the tropical Atlantic Ocean, then the water becomes relatively saltier, and then when water moves to the high latitudinal region, there it strengthens the amok because of the more saltier nature. Now that's probably what happened because of the early warming in the tropical Indian Ocean, and the warming in tropical Indian Ocean was probably triggered by the increase in insolation, which started increasing by around 20 kilo a year itself. So the early warming in the tropical Indian Ocean, which is also seen in the upwelling, intense upwelling, which might have also resulted in the increased contribution of carbon dioxide from the tropical Indian Ocean, and that ultimately affected the tropical Atlantic, and the amok strengthened. The warmer water reaching over there probably melted the sea, the surrounding ice sheets, and then subsequently a complete collapse of the amok. So here we are proposing that yes, the tropical Indian Ocean might also cause, might have contributed towards the deglaciation by affecting the Atlantic meridional overturning circulation. Thank you.
Thank you very much, Rashef. There's a time for quick questions if there is any in the chat room, or if you want to ask.
There are no questions in the chat box.
No. You can still ask in the chat box later on. Thank you, Rashef, for a very interesting presentation. If you stop sharing your screen, we may go along to the next speaker, which is Shubham Tripathi. And the talk will be about the forcing factors and anomalous behavior of the South Asian monsoon during the mid-Pleistocene transition. Shubham, the floor is yours.
Can you see my slides?
Yes, we can. Thank you.
Yeah, so I'm Shubham Tripathi, and I'm from South Asia, and we all know that the economy and livelihood of South Asia depend upon the South Asian monsoon. Our GDP is totally dependent on the rainfall occurred during the monsoon period. So this makes it very necessary to understand the variability and forcing factors of South Asian monsoon on different time scales and on different resolutions also. Particularly high resolution studies are very necessary. And especially during the period of fundamental climatic transitions like mid-Pleistocene transition, when the cyclicity, when the climate sensitivity changed from 41 kilo to 100 kilo a year. So during such periods, the study of South Asian monsoon is very important. And during my talk today, I will be describing about the forcing factors and anomalous behavior of South Asian monsoon during the mid-Pleistocene transition. So already a lot of discussion has been taken place on the Arabian Sea. But for the sake of completion, I will discuss the site setting of the IODP site 355 U1457. So this site lies in the open ocean, and it is near 17 degree north and 67 degree east, and it is around at the water depth of 3,534 meter, and it is located at 487 kilometers away from the Indian subcontinent and around 760 kilometers away from the modern mouth of the Indus River. On the southwest monsoon figure, we can see that during the southwest monsoon, a huge amount of productivity is taking place in the Western Arabian Sea, and in the northeast monsoon, there is a moderate to sporadic amount of productivity is taking place in the Eastern Arabian Sea. But the productivity, the organic matter produced during the southwest monsoon, that is during the summer monsoon, it advected towards the Eastern Arabian Sea, and there is a perpetual supply of organic matter in the Eastern Arabian Sea for whole of the year, which is responsible for the maintenance of very intense oxygen minima zone in this region, and ultimately which is causing the denitrification, which is very important process taking place in the Arabian Sea, and it alters the greenhouse gases in the atmosphere. So with this, I would like to describe the Southeastern monsoon and denitrification variability during the mid-Pleistocene transition. So I just forgot to mention the age-drift model which we developed using oxygen isotope stratigraphy. So based on this age-drift model, our data is spans from MIS 17 to MIS 35. So panel A from the bottom, it represents the LR isotope stack, benthic stack, which we have used to demarcate the various glacial and interglacial periods. And then panel B represents the denitrification during the mid-Pleistocene transition. And then panel C and panel D shows the TOC, total organic carbon and total nitrogen percent, which represents the South Asian monsoon variability during mid-Pleistocene transition. And for the sake of comparison, we took the record from Clemens et al. 1996 from the Western Arabian Sea, and it represents the lithogenic grain size. which shows the southwest monsoon strength in the Western Arabian Sea. Also, we took the delta 13C of benthic foraminifera Uvigerina to look at ventilation during that period. So we can see that during the mid and late mid Pleistocene transition, strong southeastern monsoon during the interglacial and glacial periods. So in the early phase of the so this is the early mid Pleistocene transition, this is the mid MPT, and this is the late MPT. So in the early MPT, we can see that there is a decrease in the ventilation. However, the productivity is high. So we can see strong denitrification taking place, which is more than 6 per mil value. The delta 15 nitrogen is more than 6 per mil value. So this is showing the strong denitrification. So we can conclude with this that during this early phase of MPT, the denitrification is totally controlled by the monsoon-induced productivity as compared to the ventilation. But as we move further from early to mid MPT, there is a decrease in the ventilation, continuous decrease in the ventilation take place. And after the onset of the MPT, which is around onset of the 100 kiloyear cycle, which is around 0.93 million years. And this is also the Bruns-Mutiyama boundary. So we can see that during this time period, there is an increase in the productivity as well as the ventilation is low, but there is no denitrification. So high productivity and low ventilation causes strong denitrification. But at the onset of the 100 kiloyear cyclicity, we cannot see any denitrification. So we conclude that because of the onset of 100 kiloyear cyclicity, there is a global cooling take place, extended global cooling takes place. And because of that, maybe the solubility of oxygen increased in the seawater, and that has diminished the signal of the denitrification during this period. So the denitrification is governed by southeastern monsoon-induced productivity and ventilation, except during the onset of the 100 kiloyear cyclicity. After that, the denitrification became high during the interglacial period and low during the glacial periods. So these are some of the important papers I have wrote here, like Haas et al., which has described how to divide the MPT into 3 phases, like late MPT, mid MPT, and early MPT. So the interesting thing is that the signature of mid Pleistocene transition is shown in the denitrification signal also. So after describing the southeastern monsoon and denitrification variability, I would like to discuss about the forcing factors which has affected the southeastern monsoon during MPT. So it is already described by Vikash, Kumar, and Dr. Manish Tiwari that there are 2 phenomena, dynamic and thermodynamic effects, which alters the southeastern monsoon. So during the whole MPT, I have compared the TOC, that is southeastern monsoon variability and denitrification, with CO2 concentration. And I have taken the 30° north and 30° south insolation and took the gradient of that. And then I compared the record with the precessional variability. So we can clearly see that during the early MPT, the concentration of CO2 was decreasing. However, the productivity is increasing. And we can see the amplitude of precession is high during the early MPT. So we conclude that during the early MPT, so we conclude that during the early MPT, it is the dynamical effect which governed the southeastern monsoon. And then after that, during the mid and late MPT, both the dynamical and thermodynamical effect govern the southeastern monsoon, which is shown here. So this is the mid MPT region where the productivity is high as well as denitrification is also high. And then both dynamic effects and then thermodynamic effects work in tandem. And there are some phases where they are not working together. So with this, I would like to summarize my work. And we found that variability of southeastern monsoon and denitrification during mid-Pleistocene transition is studied. Denitrification anomalously decreases during the onset of 100 kiloyear periodicity, resulting in prolonged glacial periods. southeastern monsoon was strong during the interglacial and weaker during the glacial periods of the mid and late MPT. However, during the early MPT, monsoon was stronger irrespective of the glacial and interglacial period. So the main takeaway of this work is during the early MPT, southeastern monsoon predominantly varied in response to the dynamic effect, while both the dynamic as well as thermodynamic effects governed during the mid and late phase of the MPT. With this, I would like to thank everyone for listening.
Thank you very much, Shuham, for your presentations. There has been questions, but to the previous.
Take questions.
Yeah. I have a questions actually. Did you consider, the expansion of northern hemisphere ice sheets into the count of variability in the monsoon intensity? Have you compared or contrast some of these effects, what we see in the north?
No, I have not compared with the. I have not compared with the ice expansion, but I compared with the CO2. So during this phase, which you can see here, that the onset of the 100 kiloyear cyclicity, this was the period when the climate has gained very global extended cooling, and that was because of the global expansion of the ice sheet. So directly, I have not compared with the ice sheet expansion.
Yeah.
But this CO2 decrease in the CO2 shows that that was a very cold period, and climate has gained a lot of inertia, cooling inertia, and it remained cool for that period.
Mm-hmm. Interesting. Mm-hmm. Thank you very much. Yeah, Rashef, there is a question for your talk, previous talk, so maybe you can answer them online by typing, or we get back to it after the end of the session. The next talk is given by Ramesh Kumar Yadav on the relationship between the Azore High and the Indian summer monsoon. Ramesh, are you here? Yes.
Yes.
Yes, good day. Yeah, please share your screen and the floor is yours.
Okay, sir. Can you see my screen?
Yes, very well.
Is it moving?
Yeah.
Okay. Thank you, sir. I am Ramesh Kumar Yadav. Good morning to all of you. So I will be talking about the relationship between Azore High and Indian summer monsoon. So you can see that Indian summer monsoon peaks during summer. And this is a picture of January and summertime, winter and summer. And you can see that during summer in the North Atlantic, this Azore High has attains its maximum strength, and its maximum has become much larger compared to winter. Here you can see in North Atlantic there is Icelandic low and Azore High. So during summer, as the monsoon peaks, the rainfall over this Indian region peaks, and over this North Atlantic, this Azore High attains its maximum strength, and this. So there must be some relationship between these two. So I have tried to find out the relationship between these two. So this is schematic picture of this Indian summer monsoon. There is a strong convergence over this central and northeast India, and a strong divergence at the upper troposphere. And when this divergence shifts towards west, it also shifts the whole monsoon. As this upper troposphere divergence starts this upward motion starts this convection, then this latent heat release, it intensify this tropospheric temperature, and that start converging this winds at the lower troposphere, and like that this shift with the shift of this upper tropospheric divergence, it shifts the monsoon also. So that will okay. So here means I have plotted this upper tropospheric divergence and geopotential height. So here you can see that over this Indian region, because of this monsoon, there is a semi-permanent Tibetan high over this region, which is very large. It is spans from this north of Africa to this west of this North Pacific. And here you can see there is a positive divergence that is because of this Indian summer monsoon. And over this Atlantic, there is a strong, there is a large widespread convergence. And here, as I have shown, there is an Azure high, and this is, and it is a region of strong subsidence. And because of that subsidence at the upper troposphere, there is a convergence over this, over here. So next, you can see that this is 200 HPA zonal wind and 200 HPA vorticity. So because of this represents the Asian jet stream, and this represents the American jet stream. And because of this jet stream, at the north of this jet stream, what we see, there is a positive vorticity, and south of this jet stream, there is a negative vorticity. And because over this North Atlantic, there are two jet streams. So here, there is a quadrupole type of structure in this vorticity, this positive, negative, positive, negative. So basically what I wish to say that during summer, North Atlantic is more vibrant, and its role on the Indian summer monsoon should be studied. And also here you can see that 200 HPA Rossby wave source and Rossby wave activity flux. So where there is a large scale convergence at the upper troposphere, it is the region of Rossby wave source. So you can see this region, and over this North Pacific, these are the region of Rossby wave source, and this is the Rossby wave activity flux. It is the path of the Rossby wave, and this Rossby wave comes in the this North Atlantic comes in the path of this Rossby wave. So and in this paper, for the upper troposphere, I have chosen different layer. So for zonal wind, I have taken 200 HPA level because that the zonal wind peaks at 200 HPA, divergence it peaks at 250 HPA, and vorticity also it peaks at 250 HPA, and this buoyant Varsala frequency, which is actually the measure of the stability of the atmosphere, that peaks at 300 HPA. Now, I have conducted the EUF analysis over this region, and I have excluded this Northeast India because of excessive rainfall and out of this relationship with all over India rainfall. And this is the correlation with spatial correlation of Indian rainfall with this first EOF. And here you can see that the monsoon has shifted westward. East India and Northeast India are showing subdued activities, and rest of the India, it is showing active rainfall. Then I have correlated with 200 HPA geopotential and wind. So here you can see there are these positive correlations actually represents the circumglobal teleconnection pattern, and this positive and negative, this positive and this positive center actually represents the monsoon desert relationship. And here you can see that this high pressure has shifted westward. So basically means when monsoon is active, or means it is active in the or is shifted westward and is active over this Northwest India and Central India, this Tibetan high is shifted westward. And here you can see there is another significant patch, and it is over this Azure high. So the relationship of this circumglobal teleconnection pattern with Indian summer monsoon is already known, and this is new. This is new over this North Atlantic, and that is just above that Azure high. And this is the correlation of mean sea level pressure and 850 HPA wind. So here also you can see just at the same position we are getting positive correlation. So what it basically represents that the first year, the dominant mode of Indian summer monsoon in the recent decades is related with this Azure high. So I have taken a box over this region which will represent this Azure high, and then I tried to further find out the relationship of Azure high with Indian summer monsoon. So I did this correlation again at 200 HPA and wind, that box which I have taken over this region, and then I correlated with 200 HPA. So here you can see here there is a negative correlation, negative and positive. Yes, sir.
Your 8 minutes are over.
So, so this basically represents the Rossby waves, and over this Atlantic, you can see there is a dipole type of a structure, and because of this, this Rossby waves here, you can see there is a negative, and this negative, this actually intensifies the jet stream over this region. And then I have correlated with this 500 HPA vertical velocity. It is showing a strong subsidence over this region. That is obvious because when Azure high is more intense, that subsidence will be much more. And this 200 HPA divergence means it is showing upper tropospheric convergence, and that upper tropospheric convergence will be related to Rossby wave source. So this strong this Azure high is related with this Rossby wave source, and what this shows that because of that this jet stream is much intense. Asian jet stream is much stronger, and this is burnt Wurtzbach frequency. So what it shows that because of this jet stream, this low frequency variability which are meridionally trapped and zonally elongated will travel from this North Atlantic to northwest of India. So this acts as a bridge which connect this Azure high with this northwest India, means Indian summer monsoon. So this I have done the composite analysis for excess years and deficient years. So here you can see this dipole type of a structure. This Asian jet stream is much intense than this deficient year, and also this Rossby wave pattern is much stronger respect to this negative deficient year Azure high. So during this excess Azure high is shifting this Tibetan high westward, and like that this monsoon is shifted westward, while during this deficient years this Rossby wave is much weaker, and that influence doesn't comes up to this North India, Indian summer monsoon. Now I have done this UFN analysis over this exist over the region, and it is very well it is correlated with Azure high, and this is the symmetric diagram. So how it is affecting this this Azure high is forming dipole over this at the upper troposphere, and that is intensifying this jet stream, that and this high low this high and low will shift this Tibetan high, and like that monsoon will be shifted. Thank you. For more information, you can go through this my paper, this one. Thank you. I will be happy if there is any question.
Many thanks, Ramesh. Very interesting. I can't see. Please address more questions to Ramesh in the chat or in the question and answer window later on. Thank you very much, Ramesh.
Thank you, sir.
Mm-hmm. If you stop sharing your screen, Ramesh, we can go to the next presentation, which is by Shamila Sherin on the role of the masculine high in regulating Indian summer monsoon during the medieval warm and little ice age. Shamila, are you in the room?
No, sir. Shamila is not present.
Pardon, is she here?
Similar doesn't seem to be present here.
No.
Looks like we are running too early, so people may be joining a little bit late. That is what it seems to me. Because yeah, already we are, I think, 1 hour ahead of our time, almost. Our timekeepers have been too strict.
Okay. We can have a break. Yeah, we can have a break, or we can go back to Padmasini's presentation if this has been working out.
Yeah, we can try that. Padmasini's.
Are you here? And
Yes.
will you try again to share the screen with us?
Yes, yes, I'm trying.
So if you go into the presentation mode again, then the floor is yours.
It is visible properly.
Yes, it is visible now.
Good afternoon all. As it is already discussed lot of things about Arctic climate by Manish sir and Rahaman sir. So I'll be adding one more factor about Arctic climate, that is Arctic stratification and its role in sea ice melt during the mid-Triassic warm period. As we all know, that the Arctic sea ice is melting in a higher rate, that is around 12.5% per decade, and which is a huge volume of sea ice loss. It is a huge volume of sea ice loss in Arctic, and it is observed from 1979 to 2012. So this sea ice loss in the Arctic becomes again the driver for the more sea ice melt, because of this positive feedback. As here you can see that when sea ice melts, the albedo decreases, and that causes for the more and more energy absorption, and it further increases the temperature and reduce the sea ice in the Arctic. This whole process is called Arctic amplification. So this Arctic amplification in this process, there is the Arctic stratification also plays an important role to the reduction of sea ice in the Arctic. So Arctic sea ice loss act as both a response and to a driver of Arctic amplification. So to understand the future better and to predict the future, we need to understand the past climate, which has similar climatic conditions like today. So the mid-Triassic warm period gives the opportunity to understand what happened during the past, which has similar climatic conditions. Like it has the CO2 concentration was around 400 ppm. The sea level was higher by 20 meters than today, and the SH2 was also high. So it acts as a best analog for the present climate. And so to understand, to reconstruct the Arctic stratification, we have used the sediment core collected from the Yama Plateau, that is during the ODP 151 and site 910C. This site is already discussed by Rahaman sir. This site is located at Atlantic Arctic Gateway region. Here, the Atlantic water enters, which is a very warm and saline water, enters as an intermediate water into the Arctic, which brings huge amount of heat into the Arctic. So this region, the Arctic, the stratification in the Arctic is very unique in comparison to other oceans, because in other oceans, here you can see in the Arctic, the temperature is very high in the intermediate depth, while the top is cold, and then it's warm, then it's colder. But in the other part of the ocean, the surface water is more warmer and the intermediate water is colder. But in Arctic, it's colder above the warmer water. So to understand, here is a schematic diagram. Here you can understand properly that at the surface, that is a cold and fresh water, while there is a strong halocline, then there is an Atlantic warm and saline. The stratification is basically due to the difference in salinity. At the surface, it's the fresh, and when in the intermediate, it's more saline water. That is why there is a stratification in the Arctic. And we have reconstructed how it was in the past. We have reconstructed using the relative nutrient utilization process, relative nutrient utilization. So what is the process basically? Relative nutrient utilization, that the phytoplankton uses nitrate as a nutrient. So nitrate is available at the surface. So when there are two different isotopes of nitrogen, that is 14 and 15. When the phytoplankton uptakes more of lighter isotope, that is more of 14 nitrate, that will give low delta 15 value, and that we call the low relative nutrient utilization. While when it is when it takes more of 15 nitrate, 15 nitrogen nitrate, that will give the high delta 15 value, and that is that we call higher relative nutrient utilization. So since we are talking about the nitrate utilization at the surface, so we should understand what is the nitrate concentration, how it varies in the Arctic water column. So when you see the seasonality, during the winter, the nitrate concentration at the surface is very high. That is around 11 micromole per liter, and it is very homogeneous till the from top to around 250 meter depth. While during the summer, the nitrate concentration is very low at the surface, and it increases with the depth. So the nitrate concentration, here we can see the nitrate concentration is very homogeneous during winter, while it is looks very stratified during the summer. So we need to understand this is a modern oceanography at the Yermak Plateau, but what happened during the in the past. So this is the result which I have generated. That is, the first panel is the global climatic variability, that is glacial and interglacial cycles, and the result is from 2.6 to 3.4 million years. So this this delta this second panel is the delta 15 values, which shows a relative nutrient utilization. And then this is Ba by Al, by barium by aluminum, then calcium carbonate, mass accumulation of calcium carbonate, and the calcium carbonate weight percentage. All these shows the productivity, surface productivity. So we'll see how it is behaved during the colder and warmer period. So when we see this colder period, that is during M2 glaciation. During M2 glaciation, there is low productivity, that is low values of all this, and the delta 15 values are also very low. So here we can say the relative nutrient utilization is low during colder period, and during warmer period the productivity is high. All these signals showing high, and the delta 15 values are also high. So it is showing the high relative nutrient utilization during the warmer period, that is shown by the orange bands. So why this during the colder period, why the values are low, or why the nutrient utilization is low, and why it is high during warmer period? So here we can understand properly that during this warmer period, if there is a very low mixing of nutrient or low replenishment of nutrient at the surface, there will be very less availability of new nutrient at the surface. So the phytoplankton will use any thing available in the surface. So that will take both the lighter isotope and the heavier isotope. So that will give the high delta 15 values. So from the high relative nutrient utilization, we can say that there is very less replenishment of nutrient at the surface. So it would lead to
but my 8 minutes are over.
Okay. So it will say that it suggests that there is a very strong stratification during warmer period, while it is not in the case of colder period. Colder period, the delta 15 values are low. So here we can say that there is a very high mixing of nutrient from the intermediate depth, that is nutrient-rich water, Atlantic water, with the surface. So because of that, there is a very the lighter isotopes are more available for the phytoplankton, so they will take the lighter isotope for their nutrient utilization. So that gives the low delta 15 value, and it suggests that during colder period the stratification was low. So that what causes for this enhanced stratification during warmer and during colder period? So when we see the long-term record, this is divided in three different that is colder period and the warmer period. During colder, when we'll focus on the mid-Pliocene warm period, which are major focus, we are seeing that the stratification was strong. So why it was strong? Because it could be due to there is a warmer condition. One is warmer condition, and that is reflected from the high CO2 concentration, high SST, and that is open water condition and less sea ice, which is shown by this sea ice record. And as Rahaman sir told, that is the enhanced inflow of Atlantic current to the Arctic, which could have brought a lot of heat to the Arctic, which causes more sea ice melt and the enhanced river influx to the surface. And when there is a very high amount of influx of river water and the fresh sea ice melt, that will cause the enhanced that will decrease the salinity at the surface, and that will be more fresh at the surface, which will cause for the enhanced stratification. While it is different in the colder period, because during colder period there is sea ice formation, and during sea ice formation, that will the brine rejection process will increase the salinity at the surface layer, and that the salinity difference will be very low between the intermediate water and the surface water. That will cause the more mixing of surface water and the intermediate water, and that is why there is very that is weakened stratification during colder period. And so another factor we have checked for the solar insolation and the what was the controlling forcing factor. So from the spectral and wavelet analysis, we have found that there is a strong periodicity around this 3.1 to 3 millennia, which is eccentricity cycle, and it suggests that the major forcing factor would be the eccentricity cycle, which cause for this reduction of sea ice or enhanced stratification at the start site. So, so when there is a strong stratification at the surface, so that will absorb more and more heat during the warmer period, and that will accelerate the sea ice melt in the Arctic. So the stratification also play for the sea ice melt, and so in future, if since the global warming is continuing, so that will then we'll get the more fresh water at the surface in the Arctic in the future. Thank you so much.
Thank you very much, Masini. Very nice, very interesting. We have time for questions if there are any in the audience. I have myself. Will you continue to explore this site, or did you try to compare with some modern Holocene sections in nearby your site, just to verify your observations for this interglacial glacial cycles you see?
Yeah, there is already one study by Subatata 2001, which has shown like when there is a colder period, the stratification is very weak during the last glacial period. So they have not during the Holocene, in comparison to Holocene, there is a strong stratification in the Arctic Ocean, but not exactly at the Yamak plateau. But there is no long-term record about the stratification. So,
But are you still working on this site from Yamak Plateau, or is it concluded? And
I have not continued, but yeah, I have not worked anything. So like again, we are like now comparing with the monsoon and we are seeing the Teleconnections.
Yes. Very good. Interesting. Thank you very much for your presentations. If you stop sharing your screen, we are a little ahead of time, as Manish said. Manish, would you suggest to continue, or shall we have a short break, or what is your advice?
I think only 2 talks are remaining. So let us try to have them. so that, yeah. So
the question was whether Sharmila is in the panel list
I think
now.
she is there. Just check again.
She has joined.
She has joined.
She has joined. Very good. Okay, then we continue with her presentation from the Mascarene High. So if you share your screen, Shamila, then the floor is yours.
Yes, sir. Can you hear me?
May you speak a little louder or get closer to the microphone?
Can you hear me now?
Yes, very good. Thank you.
Okay, so I'll share my screen now. Is this visible?
Yes, it is. Thank you.
Hi, I have been working on the role of mascarene high in regulating Indian summer monsoon during medieval warm period and little ice age. We already know that mascarene high is a semi-permanent subtropical high in the southern Indian Ocean, which has a tremendous role in influencing Indian summer monsoon through the availability of moisture by cross-equatorial wind convergence. And a stronger high pressure over mascarene high would cause a stronger cross-equatorial winds and enhanced monsoon, while a weaker subtropical high over mascarene high will cause the impeding of winds, and in turn it will affect the strength of the monsoon as well. Little research has been conducted on mascarene high's role in regulating Indian summer monsoon over a longer time scale. We aim to provide a better understanding of the influence of mascarene high over Indian monsoon over the last millennium. We are already aware that last millennium there was this period of medieval warm period and little ice age. Medieval warm period was a period of warmer climate over North Atlantic and over globally from 950 AD to 1250 AD. And it was followed by little ice age, a cooler period of climate. A variation in solar activity, volcanic eruptions, oceanic circulation, etc. were the reasons of the change in the climate over this period. As this picture, you can see the sea surface temperature anomaly over medieval warm period and little ice age over last millennium. Uh, so I'm sharing some previous studies that has been done on how the Indian summer monsoon rainfall have varied over the last millennium. These are a study that has conducted with various PMIP3 models of last millennium, and the anomalous rainfall over the periods have been plotted. You can see a higher anomalous rainfall over medieval warm period and a lower anomalous rainfall over little ice age on various PMIP3 models. This is another study by Vidya PJ et al., a recent one, where they have pointed out how global warming hiatus contributed to weakening of the mascarene high in the southern subtropics, and how the impacts are affecting the Indian summer monsoon over the periods. You can see the intensity varying over the recent years from around 2000, and how the sea level pressure gradient between mascarene high and Indian subcontinent has varied over the recent years. So as we have conducted the study, we could see that the sea level pressure gradient between mascarene high and Indian subcontinent, you can see how it is varying over the years. During medieval warm period, we could see a higher annual sea level pressure gradient over the years, while little ice age, it shows a sea level pressure gradient lower than what was shown for medieval warm period. And the anomalous rainfall over Indian subcontinent has also shows a similar result with an enhanced monsoon over the first part of the last millennium, while later parts shows a reduced rainfall during the time. And as a coincidentally, the cross-equatorial wind at 850 hectopascal also shows a similar trend. During the medieval warm period, we can see enhanced cross-equatorial jet between mascarene high and Indian subcontinent, while during little ice age, the cross-equatorial jet is showing a weaker trend. So this is also can be correspond to the rainfall and the sea level pressure gradient over these same years. AMO, we already know that the rainfall, Indian summer monsoon rainfall on a multi-decadal time scale is often linked to the variability of Atlantic multi-decadal oscillation. As we already know that AMO is a variability in the sea surface temperature over North Atlantic and over a time scale of decadal time scale. So when we plot AMO index overlaid over the anomalous rainfall, we can see that over the initial years of last millennia, for the medieval warm period, we can see AMO and anomalous rainfall following a negative correlation with each other. As we already know that now the AMO for a positive decadal phases of AMO, the enhanced monsoon will be enhanced monsoon is available for over India. But during the medieval warm period, we could see that for the positive periods of AMO, the monsoon was anomaly was reduced, and later for the years of little ice age, for these years, AMO and rainfall is shown to vary almost similarly. So we have found the rolling correlation between AMO and rainfall. It shows a negative rolling correlation for the years of most years of medieval warm period, and we can see a positive peak for little ice age over the Mondor minimum that period. So this is the spatial correlation between sea level pressure gradient between Mascarene High and Indian subcontinent. The spatial correlation is calculated with anomalous rainfall over the region. We can see that medieval warm period shows a higher spatial correlation with Mascarene High. The rainfall is showing a higher correlation with the sea level pressure gradient between Mascarene High and Indian subcontinent. The same way, little ice age, we can see that the sea level pressure gradient is influencing the rainfall considerably lower comparing to the medieval warm period. And we can compare this result with how the AMO and rainfall has AMO has impacted the rainfall. We could see that during the initial years of AMO, the last millennium, AMO was negatively correlated with the rainfall, while the Mascarene High has a higher impact on the rainfall. So maybe the Mascarene High's competing effect was overshadowing the effect of effect posed by AMO, and these are the key takeaways. The enhanced mean sea level pressure gradient between Mascarene High and Indian subcontinent is consistent with the strengthened Indian summer monsoon over medieval warm period, along with strengthened cross-equatorial winds. Reduced rainfall over a little ice age is attributed to weakened cross-equatorial pressure gradient and a weakened cross-equatorial winds. Spatial correlation of sea level pressure gradient between Mascarene High and Indian subcontinent with Indian monsoon is higher during medieval warm period and lower during little ice age. We can deduce that Mascarene High having a higher influence on monsoon during medieval warm period and lower influence on monsoon during little ice age. So these are the points that I wanted to say.
Thank you very much, Shamila, for a nice presentation. I don't see any questions in the chat room, so thank you very much again, Shamila. We are approaching the final presentations in the session, and this is given by David Bonan and Edward Blanchard-Riggle-Worth on the potential glaciological site survey to determine an optimal coring site in coastal joining moorland in Antarctica.
No.
No?
Yeah, there's some confusion that David Bonan or Edward Blanchard will speak on non-stationary teleconnection between the Pacific Ocean and the Arctic sea ice. So there was a swapping of the talk, yeah.
Oh yeah, sorry, I didn't get this. Right.
So the only thing is whether they are there or not, because it must be very early morning for them. Yeah. around 4 o'clock or 5 o'clock in the morning. So
You're right.
So just check whether Vikas, can you check whether David or Edward are there?
I just checked, they are not there.
Because they informed me that it will be very early morning, so I kept their talk in the last. But since we are running a bit ahead, so
shall we wait a little bit, have a short break, or?
Yeah, maybe.
Mhm.
Because the audience is also there, they may also need to.
Yeah. So Manish, you suggest to have a 10 minutes short break and see whether Edward or David appear?
Yes, but the only thing is how it will go. Means we cannot leave the session. We have to wait here only. So
yeah, we can.
We will come after 10 minutes. We will stay online.
We stay online. We convene at within 10 minutes time.
Yeah, and see whether he's there or not.
Yeah.
6 p.m. IST.
6 p.m. Okay.
You still ask the questions to the previous speaker. So if you want to use the chat room or so, please raise your questions.
So
Amban has a question. Yeah.
Yes. My question is to Sharin. Sharin, I just saw that some interesting presentation on Mascarene High during the medieval warm period and then comparing with the Little Ice Age. My question is that actually, so you mean to say that actually when you say that during medieval warm period, they had a better control on monsoons compared to that of the Little Ice Age? What does it mean for the future in a more warming world? What does it mean for the future?
Shabila for some reason seems to be disconnected.
Vikas, can you answer that?
I didn't get the question.
Question is that actually she was saying actually that the link between Mascarene High and monsoons, Indian monsoon is strong during the medieval warm period and not strong during the Little Ice Age. Am I right with that? That statement is correct?
Yes, sir. I will have to confirm with because I don't have the slide with me right now. But the aim of this work, what she was trying to do is that she was looking. We have looked at Mascarene High, how it affects monsoon using the reanalysis data, which is over the modern time period. But nobody has done any past study. And also in the modern data, although we see that Mascarene High couples very well with the dynamics or the circulation part of the monsoon.
But she was showing the graph with medieval warm period and Little Ice Age.
Yes. So so she had shown various plots of medieval warm period and compared it with the Little Ice Age, where she was showing that during medieval warm period, monsoon was stronger and the Mascarene High, the cross-equatorial pressure gradient was.
Exactly. That's my question starts from there. So what does it mean for the what you call future climate? Is it going to be more stronger, this relationship, or is it not straightforward?
So if we just consider the last 1,000 years, going by that, we in the warming world, if warming continues, we will expect the Mascarene High to be more coupled with the monsoon. But that is just, we will have to look further into even a longer time scales and look into other ways to see
because actually you see that medieval warm period was a natural warm period actually. Now what we have the warm period or which is going to increase or increasing is not natural at all. So it could be there different forcing itself to go inside.
So was it a one-off event or will it continue as a general trend? That is something which we will ponder over and see.
Right. Anyway, okay, thanks.
Maybe we are all here. Manish, are you still in the room? You could not conclude your talk, and it was very interesting for me to see how you finally conclude on the connection of the Arctic to the Arabian Sea. So maybe if you could share your very last slide.
Yeah. the most interesting slide was not allowed to be presented.
No, exactly. So if you
Okay.
could guide us through.
There's a poor time management.
No. This is the minimum time I require, depending on the work.
Because you are the convener, so you asked everyone 10 minutes, so you would not get more than 12 minutes.
That is why I stopped that. Okay.
So you have enough.
We have enough time, so we will.
I give you another 5 minutes, Manish, if you guide us
great.
through us this slide views.
Okay, so what I was talking that there are thermodynamic and dynamic effects. Thermodynamic effects is basically which affects the specific humidity, which is the global temperature change due to PCO2 variability. And then there are dynamic effects which causes variations in the atmospheric mass fluxes because of the non-uniform temperature change, basically the meridional temperature gradient, which causes ITCZ migration. And these effects can be because of the orbitally modulated insolation, Arctic sea ice extent, or anything which is causing northern hemisphere or northern polar region or southern polar region cooling or warming, and SST. So SST variability in the tropical Indian Ocean and Arabian Sea. So what we did that during the Pliocene, so the scale below at the bottom represents the late Pliocene from 2.6 to 3.4 million years ago. And here we have compared our proxy record of monsoon variability, which is shown by this record, this red color curve. And we have compared it with various forcing factors, which is for example, here is the first panel is the insolation. Second panel is the sea ice concentration. And the third panel C is the PCO2 variability and the glacial-interglacial variability based on LR04. So now this monsoon variability is a interplay of all these factors. So we have to look them one by one. So when we go to the first panel, so whatever proxies, whatever forcing factors are supporting the monsoon variability, those I have shown by the arrows, and where they are not supporting, the arrow will not be there. So let us take the example of the interval 4. Here the monsoon is weaker. During the late Pliocene, interval 4, the monsoon is weaker. At that time, we find that PCO2 is also declining. The global cooling is happening. There is a very severe glaciation, the M2 glaciation. And at that time, the Arctic sea ice extent is also showing a increase. So this decline in the monsoon during the interval 4, very, very clear-cut decline, which is seen in the proxy as well as in the simulation data. So this decline can be explained both by the thermodynamic effect, that is the CO2 decline and the decline in the global warmth, as well as by the Arctic sea ice increase also. So how Arctic sea ice increase will affect the monsoon? So there are various mechanisms proposed. For example, by Schneider et al. 2014 Nature paper, they have shown that whenever we have higher Arctic sea ice extent, then there is a northward transport of energy from the northern tropical boundary. So that northward cross-equatorial, when there is an exchange of energy from the northern tropics boundary, then to compensate that, there will be a northward cross-equatorial energy flux from the southern hemisphere, and that will cause a southward shift of the ITCZ. So whenever the northern Arctic, the Arctic is getting cooler, at that time the tropics are losing energy to the Arctic, and ITCZ is responding to the interhemispheric energy asymmetry. So at that time, the ITCZ is shifting southward, resulting in a decline in the monsoon. So at that time, both the thermodynamic effect as well as the dynamic effect by Arctic sea ice and by the insolation, they both are showing, causing the monsoon to decline. Then we come to the mid-Pliocene warm period, the interval 3rd. During that time, in the early part of the mid-Pliocene warm period, we see that the monsoon is on the higher side. So during the early part, the solar insolation is increasing, so that supports the high monsoon. At that time, we see a very high increase in the PCO2 also, and the global warmth is also increasing. So the high monsoon, though the Arctic sea ice is higher, so it should have reduced the monsoon. But because of the thermodynamic effect of PCO2 and of the insolation, the monsoon is higher. When we come to the later part of the MPWP, we see that the insolation has decreased. At that time, the CO2 has also decreased. There was a global cooling, KM2 glaciation. So the monsoon should have shown a weaker signature. But we find very strong monsoon in the simulation as well as proxy data. So which can be explained by the high Arctic sea ice extent. Then we come to the next period after the MPWP, when there was a cooling. At that time, there was very high, the monsoon was weak, quite weak. And at that time, the CO2 was reducing, CO2 was quite low, and the global warmth was also declining. There was global cooling. So this supports the weak monsoon, though the insolation was on higher side, but still the this thing was weaker, the monsoon was weaker. And when we come to the and the Arctic sea ice extent also at that time is supporting the weaker monsoon. This increase in sea ice supports a weaker monsoon. So at that time, both the thermodynamic and dynamic effects were supporting weaker monsoon. This was a condition when the high Arctic sea ice, so how it can reduce the monsoon. Likewise, when there is low Arctic sea ice, for example, in this period. So this period I have already told, the period 1 at 2.95 million year, there was a global cooling. As you can see that the CO2 was declining, and there was this is known as the intensification of the northern hemisphere glaciation. So during this time, the monsoon is supposed to decline, but we find very intense monsoon. So this is because of the ITF variability, which I had described in my talk earlier. But during the later part of this interval, we find that monsoon is still strong. This may be because of this decline in the sea ice. So whenever sea ice is declining, it is supporting higher monsoon. This one mechanism was proposed by Chatterjee et al. Recently, that whenever there is lower sea ice, there will be reduced pole to mid-latitude temperature gradient, and that will modulate jet stream flow and circulation. And via Rossby waves, it will cause a stronger East Asian subtropical high, which favors higher precipitation. So lower sea ice favors higher precipitation, whereas when we have high Arctic sea ice, the ITCZ shifts southwards and we get lower precipitation. So this is how there is a interplay of sea ice, northern high latitude temperatures, and PCO2 and insolation, how they govern the monsoon. So based on this, I had given my takeaways that during the late Pliocene, there were two distinct intervals of monsoon intensification, MPWP and 2.9 million years ago because of ITF variability. Then whenever lower Arctic sea ice extent is there, a stronger Pliocene South Asian monsoon, it supports a stronger Pliocene South Asian monsoon, based on which we can say that in future with continued warming and declining sea ice extent, more intense precipitation, though regionally varying. That was very interesting in my what we found in our simulation, that what is the modern trend that we are seeing, which is the horseshoe pattern, that is reflected in the MPWP simulation as well. There is higher precipitation over the Western Ghat and over the core monsoon zone, but lower precipitation over the in a warming scenario over the Indo-Gangetic Plain and the Northeast monsoon. So yeah.
Thank you,
So
Manish. There are questions in the question and answer room. You discussed that Indian monsoon strength at 2.9 million years, possibly due to changes in the intertropical front from warmer to colder tongue. But these changes took place around 5 million years. So what possibly acted at 2.9 million years with the reference?
Yeah, so at 2.95 million years, there are references which show that there is the New Guinea shift is there. Tectonic shifts are there, which cause the, I think I have explained this in my earlier this thing. Yeah, so there is a tectonic northward shift of New Guinea, which caused the source water of ITF changes from the warmer South Pacific to the colder North Pacific. So the references, there are several references by Karas et al., etc., which are given in this paper, Sarachand Prasad et al., 2021 PPP. So when this cooler water from the relatively cooler water comes to the masculine high region, that increases the cross-equatorial pressure gradient and temperature gradient, which results in higher monsoon during that time period.
There's another question to you, Manish, about the contradictory observation of the delta 15N and the sea ice. You may comment on these questions as well.
I'm able to not to see the question. Okay. Arctic sea ice seems to be responding to 15 and summer insolation. Higher insolation variability coincides with the lower sea ice and vice versa. But the delta 15 and proxy monsoon doesn't match with the sea ice trend. Increased monsoon leads Arctic sea ice decrease. Layer from predict hypothesis of low sea ice and intense monsoon. Monsoon doesn't match with the sea ice trend. What he's trying to say, Arctic sea ice seems to be responding to delta 15 and summer insolation. Arctic sea ice seems to be responding to 15 and summer insolation. 15 and summer insolation. Okay, you're trying to correlate with 15 and summer insolation. No. This Arctic sea ice is not responding to the 50-degree north summer insolation. The Arctic sea ice is basically responding to the transport of the North Atlantic water by the North Atlantic current, as Rahaman had shown. So this Arctic sea ice is basically responding to the processes occurring in the North Atlantic, not to the 15-degree north summer insolation. So that is the case. Okay, I think this is what.
There's another hand raised by Rajev.
Yeah, Rajiv. Yes.
Yeah, Manish, interesting. I just want to know, like, there are several papers coming up now that probably it may be the opposite way. Right now, what you're trying to figure out is that, rather pointing out, is that the Arctic sea ice variability affects the monsoon. But is it possible that the monsoon affects the sea ice variability or the thermal circulation? Of course, there are modeling papers as well as some proxy data also suggesting the same.
Yes. Very pertinent question. And I had in the beginning itself told that in fact to the introduction to the session, I had told that it is a two-way street. The northern higher latitudes are affecting the tropical regions, and tropical regions are also affecting the higher latitudes. In fact, I had shown one slide. So my slide is getting stuck due to some reason. So every time I'm trying to show something, it is getting stuck. So yeah. So when I was discussing the present day studies, at that time I had shown one slide. So this paper, where this paper discusses that how during the extreme summer monsoon events, there is large amount of heat input into the atmosphere, and this heat anomaly is transferred to the Arctic region, over the Canadian Arctic region, basically, which reduces the Arctic sea ice. So in fact, yes, monsoon is also affecting the Arctic sea ice, but on the other hand, there are studies which shows that Arctic sea ice is also affecting this study by Saurav et al. That Arctic sea ice is also affecting the monsoon. So it is a two-way street, certainly.
I mean, as a broader community, say, let's try to look at whether it is possible in some way to make out what is affecting what, or we will still keep on correlating our data with whatever suits well. I mean, there has to be some way forward over here.
Yes. That is an important point, no doubt.
Somehow we really
maybe see the biggest problem in our basically paleo data is that the chronology. So whatever the uncertainties with the chronology, we cannot compare the lead lag relationships. So if we get into lead lag relationships, then we can get to know what is causing what. But because of the uncertainties in chronology, it is very difficult. Jochen, your views on this?
We have always the same problems, chronology for these older sections. So beyond radiocarbon ages, it's getting more and more difficult.
Yes.
Waliur, you have a question or comment?
Yeah, so, but then monsoon, basically the precipitation, but then none of the actually proxy presented here actually directly reflect the precipitation. So most of the productivity based.
Waliur, that is why they are called proxies.
Even in the proxy, it is a proxy's proxy. So
ultimately, all the proxies have some limitations.
So,
and
coming to the question is actually in the Arabian Sea setting, when we talk about the productivity and directly we infer about the monsoon, but then you have a huge amount of dust flux and some other processes, which is also affect your productivity. So let's say even in same scenario, I can create in arid condition, means productivity, or by your increasing monsoon. So if you have a high dust flux, you can produce more productivity.
It is very well established based on satellite data, based on sediment trap data, based on sediment core data, based on in fact observational studies that during the South Asian monsoon, during the summer monsoon mostly, productivity increases in the Arabian Sea. So productivity established as a proxy for Arabian Sea for a long time, and several papers on there, in hundreds you can count. So there can be problem that productivity can be affected by the preservation. That maybe redox condition, change in redox condition can influence the organic matter preservation, etc. But overall, organic matter content, etc., is very well related with monsoon. So they are taken as a monsoon proxies very confidently. Yeah, of course, all those things can also cause productivity to increase, but the dominant effect is because of the monsoon. That is the.
I will stop a bit discussion here because before I give the word to Rashif, is David or Edward in the room now? Just to check again before. Yeah. Mm-hmm.
Otherwise, we will get carried away and.
We carried away, and we can just discuss it within a small group, which it's nice, of course, but yeah. Let me see. Like. Can the IT group help me?
Edward is here.
Edward is here. Okay. Good morning, Edward. Very early in the morning, I suppose.
Request the IT team to let him in to the panelist group.
Can the IT help me with this? If you hear me, Edward, and you are able to join the panelist, then let me know. Until this is the case, Rashif, you had a questions to Manish. So if you would like to address this question.
No, Jochen, I think he has joined. You can ask him to present. Edward is here.
Okay, Edward is here. Nice. Edward, there you are. Good to see you. Early morning, I suppose. So hope you're ready to share your screen with us.
Hi. Yeah. Hi, everyone. And thanks for your flexibility with the scheduling. And it's quite early, but a little better than 3 in the morning.
Take your time.
I'm ready. Yeah, I'm ready to present whenever.
Yes, you can share your screen and present your science with us.
So I hope you can see just one slide, right? Hopefully this.
You have to go into presentation mode. We see.
No, is it still? I've had. Okay.
Yeah, looks good.
Okay. Hopefully this. Okay. Does this work?
Yep.
Great. So yeah, thank you for the opportunity to speak in this session. And I want to talk about some work I did with. I'm a faculty member in the Department of Atmospheric Sciences at the University of Washington in Seattle in the US. And this is some work I did with Dave Bonan, who was a student of mine at the time, an undergraduate student. Dave is now doing a PhD at Caltech in California Institute of Technology in the US. And we've been investigating a teleconnection between the Pacific Ocean and Arctic sea ice. And the other kind of key word in the title is non-stationarity, which will give you a hint for some of the analysis I'm going to show. What is the summertime Pacific Arctic teleconnection? This is a teleconnection that we see in observations, and it's a relationship between between September sea ice extent and sea surface temperatures in the preceding June, July, and August. So this is sort of from summer SSTs to September sea ice extent, and it's been published in the literature in a couple of different papers in recent times, Baxter 2019 and Dingendal 2019. And what I show you here in the top map, this is a correlation map between September Arctic sea ice extent and SSTs at every grid cell. And you can see that where the grid cell is stippled, that means that the correlation is significant. And this shows you basically that there's a positive correlation between Arctic sea ice extent and June, July, August summer SSTs in the sort of central, kind of in the subtropical northern central Pacific, and that kind of a bit of a horseshoe, but especially extended between basically California and Mexico towards Hawaii and past. And basically this means that when SSTs are positive, somewhat counterintuitively, this leads to positive sea ice, to more sea ice in the summer. And the mechanism behind is shown in the low panel, and that is, we show here the correlation between June, July, and August SSTs in the green box and Z200 geopotential heights. So basically, when there's a positive SST anomaly in this region in the Pacific, in the Arctic we see lower, like cyclonic heights in the troposphere, and these tropospheric conditions are favorable for sea ice gain. So we see this atmospheric bridge going from the Pacific to the Arctic. And the mechanism is more or less due to this schematic, where you have, if you have, this is actually showing if you have cool SSTs, which would lead to less sea ice. So with cool SSTs, we have lower convection over the Central Pacific, and this kicks off a Rossby wave, which in the Arctic results in higher geopotential heights. And this is for the Arctic, it's sort of well known that a high pressure over the summer leads to more sea ice loss due to two things. One is adiabatic heating of the column through compression of the air column, and then you have less cloudiness, so more sunlight reaching the surface and more sea ice melt. We were interested to see then, do climate models show this teleconnection between the Pacific and the Arctic? And I'm going to look at we looked at CIMIC 5 models in this work, and then the other research question was, well, in the observations we only have about 40 years. Is this a long enough period to say something about this teleconnection? And so we look at how this teleconnection varies in time. So starting with the CIMIC 5 models, what I show you here are the same two maps as before, but now showing you the average of all CIMIC 5 models. I think we used about 23, 25 models. And for each one, we used at least 200 years. So it's a huge amount of data. Statistically, it's very robust. And what you can see here in the top panel, we correlate, the top panel is the correlation between September Arctic sea ice extent and summer SSTs. And you can see that most of the globe, the color is white, which means there aren't any teleconnections, right? And there's definitely no positive SST anomaly here in the Central Pacific like we see in observations. So from a modeling perspective, when we look at the full time periods, very large data sets, and average across all models, we see that there is no link between Arctic sea ice and summer Pacific sea surface temperatures. And when you do the second analysis, when you look at the correlation between the Central Pacific sea surface temperatures in the green box and the Z200 geopotential heights, you can see there's no atmospheric bridge to the Arctic, right? So higher SSTs do cause higher heights across the tropical belt, but there is no, there's a little bit of a Rossby wave propagation to the south. You can see the Rossby wave, the wave train here going south. A very weak one maybe going to the North Pacific and Alaska, but nothing to the Arctic, right? So there is no, the Pacific SSTs are not forcing any atmospheric variability in the Arctic. Helping explain the fact there's no teleconnection in the sea ice to the SSTs. Now, when we look at the historical, those were from control runs in CIMMYT 5. Now, if we look at the last 40 years in CIMMYT 5 in the modern period, we see a very similar result. So I'll just toggle back and forth. This, the lack of a teleconnection is still a feature in CIMMYT 5 models in modern times. Now, something we found very interesting as we start to dig into individual models was the fact that individual models can actually give you very different patterns. And what I show you on the right, in these two panels on the right, this is the correlation between September sea ice extent and global SSTs in the summer. And in two different models. In the top is CCSM4, and in the bottom is CMCC. And you can see that if you look at the Pacific, the patterns are actually the opposite. So we have different GCMs with very different patterns of SST link to Arctic sea ice extent. And then this leads us to the questioning is like, well, do the observations, do they sample a sort of extremalization? In other words, have the last 40 years been unusual, or would they be common of, say, if we had hundreds of years of observations? Because going back to these model results, you can see that even though long periods in model mean don't show teleconnection, individual models can. And so we address this question of stationarity. One way we address this is that we look at the very long simulations from the climate models, and we pick 40-year running windows, and we do a pattern correlation between the Pacific SST patterns in the model and the observed teleconnection on the left. So basically, in this case, for example, we take the map on the right and the map on the left, and we calculate a pattern correlation, which gives you one number between -1 and 1. And if it's 1, then it'd be a perfect match. If it's -1, it'd be a perfect anti-correlation. And you can see that, you can probably visually see that you might get a negative number if you do the pattern correlation of these two figures here, right? Because on the right, you have the negative anomalies, while on the left, you have the positive anomalies in the Central Pacific. So when we do this, we find exactly that. And this time series is basically a time series of that pattern correlation during different 40-year running windows, right? So you can see that CCSM4 during this specific window, which is the last 40 years of the historical run, has this negative pattern correlation, but it actually oscillates between 0, fairly strong positive numbers, and negative numbers, right? So basically, this teleconnection, at least as simulated in models, is highly non-stationary, and you can go from periods where the Pacific SSTs can either be positively correlated or negatively correlated to the September Arctic sea ice extent. And we have seen that that is fairly characteristic of all models, right? So we've done the similar calculation with every model. And when we calculate these time series of the pattern correlation, we calculate a mean, the interquartile range, and then the extremes. And that's what we show in this panel here. And you can see that a lot of GCMs in terms of the mean teleconnection around 0, which is what we expect from the original figure, because if you look at long time periods and all GCMs, we know there is no teleconnection in those models, but a lot of models can swing from pretty high values around 0.6 to minus 0.6 or even minus 0.8. And just to illustrate that, this is, for example, the positive extreme with the HADGEM2 model. And you can see on the left, this is the SST correlation to Arctic sea ice extent, and this is on the right, the Z200 and the atmospheric bridge. And you can see these patterns actually look very similar to the observed patterns. And then you can also pick a negative extreme from the BCC model, and you get pretty much the opposite. And this is my last slide. We see a little bit in the observations, we do see some evidence of this non-stationarity in the actual observed teleconnection. And so what I'm showing here are the same maps as before. These are the correlation maps between summer SSTs and Arctic September sea ice extent. And on the left are the first 20 years of the observed period, and on the right are the last 20 years. So you can see some evidence that this teleconnection, even in observations, might be highly non-stationary. This has some implications for predictability if we want to use summer SSTs in the Pacific to predict the Arctic September sea ice extent. That relationship might not be as robust as we believe it from the observations. There are remaining questions about the role of model biases in coupling and Rossby wave propagation and Pacific convection. And that's for future research. And thank you for your time.
Thank you, Edward, for your talk. Please raise your questions if you have any. Yeah, Rasha, if you have a question.
Yeah, Edward, interesting talk. In fact, before you joined, we were trying to discuss the same, like whether it's the polar ice which affects the SST or the monsoon in the tropical oceans, or it's the tropical monsoon which affects the sea ice or tropical SST. Now, again, the observation seems to be like it's not a consistent relationship. That's what I'm trying to get. Am I right?
Exactly.
Okay.
And for 40 years, I think when you look at climate models, which, you can run a climate model as long as you want, in the control runs, we have 1,000 years. And when you start to compare 40-year periods with 1,000-year periods, for some processes, yeah, you can see they're very stationary, they're very robust. And I think sometimes with teleconnections to the Arctic or from the Arctic, we see that the more tenuous, the less robust. When you look at maybe the full period, they are very weak or they don't exist. And when you go to shorter and shorter time intervals, down to about 40 years, maybe even 50 years, sometimes even up to 100 years, you can find these patterns that do look strong and meaningful, but maybe the next 100 years or the next 40 years don't show that pattern. So I think that's a good thing to remember when we look at observations and only 40 years. And we see a similar thing with Antarctica. Teleconnections from maybe the Pacific to Antarctica, that there are periods when they're stronger and other times when they're weaker, and they can last decades. So I think it's a good thing to remember when looking at just a short observational time series.
Okay. The second question related to that is, like, you only focused on Pacific, but does this also apply to, say, tropical Indian Ocean? I mean, I did see that, yes.
So that's a great question. And maybe if I go to the beginning, I think I'm still sharing. So at least for September sea ice extent, if you look at the Indian Ocean, there's not really any correlations that show up. Maybe for the south of Madagascar here, there's some negative, and even for the south, there seems to be a bit of a dipole here between the SSTs. But is that noise, or is there a real mechanism? you know, I think sort of looking at the models would seem to show that there's nothing very strong. There's no very strong teleconnections between any tropical SSTs and September Arctic sea ice extent. And again, this is in interannual variability, right? So we're taking the time series of Arctic sea ice extent in September for every year. The low frequency might be different, right? So you might have an ocean pathway, you know, and this depends on an atmospheric bridge, right? Like an instant force in from Pacific SSTs or tropical SSTs to the Arctic, right? Now, if you looked at the low frequency, then you might have an ocean pathway through ocean currents, and maybe on centennial or millennial timescales, you might have a link. But this, you know, this analysis wouldn't pick that up because, you know, we're just interested mostly in interannual variability of the Arctic sea ice extent. That's a very good question. I think there's a lot of research, mostly for the Atlantic, right? There's research looking at AMOC and Arctic sea ice extent. As I don't know as much looking from the Indian Ocean to the Arctic.
Thank you.
Thank you very much, Edward, for your presentations. I think we reached the end of the session. So Manish, if you want to say a few final words.
Yeah, so first of all, we had a great marathon session lasting around 4 hours and covering various spatiotemporal scales. So we covered from Antarctica to Southern Ocean to Indian Ocean and went to Arctic and now to Pacific as well. So after that, we covered the various temporal scale also from ice core spanning 200, 500 years, the present day observational data, model data, reanalysis data, and then proxy data on million-year timescales. So in our session, there was something for everyone. And with that note, I would like to thank all the speakers who made this session successful, all the attendees who sat through the session, and finally my co-conveners for helping in this session. Thank you all.
Thank you. Thank you and goodbye.
Bye-bye. So we'll leave now.